Boop. Yep, sure is. Hmm. We have a totally different view, as you were saying today, and a totally different viewpoint.
Yes. And a lot of people from the last two classes
That
or the
is not,
last.
well, some people wanted to do the whole thing. I mean, I don't know what it'd be like listening. I could ask my wife, I guess, what it's like listening to me for 18 hours. Probably awful. So
That's why she
kudos.
says you sound like whoa, 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 whoa,
Yeah,
whoa, whoa.
exactly.
But as one who has signed up for both classes, even though I already have my tech license, it's a great review before you go on to do your general stuff, even if
So
it is 18 hours.
yeah, but yesterday was helpful, I hope, or the last
Yeah,
2 days.
Last one.
yeah.
I the thing is that I have the viewpoint of somebody who got his license by studying the book and learning everything as I
You
went
signed
because I
up.
was in college and been 40 years on the air and work, and I mean, I've worked in industry for
No.
25 years, buildings or 20, yeah, 25 years
Oh, I
building
was wondering
equipment.
whether you passed your test.
Scott,
Yeah,
before we start, can you take a note of this, please? G5C06.
one more time, G5
C Charlie 06.
06.
Yes,
G5 Charlie 06. G5
yes,
Charlie 06. Golf 5 Charlie 06. It should be able
that's
to
it. Yeah,
uh let's see. I'm looking at the wrong book. That's why it's not there. Golf 5 Charlie 06. What is the voltage output of a transformer with a 500 turn primary and a 1500 turn secondary? 100 turn. Okay.
mm,
Yeah, that's right.
mm. I'm not
What
quite sure to get it right, to get this right because it says the right answer is 360.
it is 360.
But
It is.
I do not agree, to be honest.
Here it is. We have 360 volts, or sorry, we have 120 coming in here. It absolutely is. This is a step up transformer. 120 volts. You have 500 turns, and you have
It's not a step
1500
up.
turns.
It's
1500
not a
turns on
step
the
up.
secondary.
No, it's a 500 turn primary.
Yeah, this is the primary.
Yeah, and the 1500 turn secondary.
Right. That's a step up.
Right.
So the
Okay.
turns ratio is 1 to 3, not 3 to 1. You'll have 360 volts here. It's a
Mm,
step up, not a step down.
500 primary and 1500 secondary. So it's a step up or step down, and I don't get it.
Because this is N2 and this is N1. This is V1 and V2 and N2 over V2. And let's not do it that way. N2 over N1 is equal to V2 over V1. And V1 is
Right.
120. And this is 500. And this is 1500. So to make that right, this must be 360.
So what part of this didn't come with the question?
Question is
Z50C06.
yeah. The thing is, if you flip the transformer around, then it's a step down transformer.
Yeah, but it says 500 primary and 1500 secondary.
Mhm.
So why you are saying V2 over a ratio of Y V1 and not the other way around? I don't get it.
That's how transformers work. The voltage is proportional to the number of turns in that coil.
Yeah, but why V2 ratio with 1 and not the other way around? To me, it would be 500 ratio 1500. It's not divided by. No,
Well, okay, I can flip that. I mean, I can.
Yeah, you can. Yeah, but
and it comes out the same way.
no. The question is primary over the secondary. So 500 over 1500. I don't get this.
Right? Do you agree that that's right?
I do. Yeah. Okay.
Okay. N1 is 500. N2 is
Yes.
1500. And V1 is 120 volts. And therefore, that must be 360. Now, the current is inverse, and that's because of power. Because P is equal to EI or VI, depending on how you write it.
Yeah, no, that's okay.
So that flips the relationship. So your current is going to be inverse because of conservation of energy. Because the power in has to be very close to the power out. And because the
Good morning, everyone.
Morning. And because the current goes up, or sorry, because the current goes down and the voltage goes up, the apparent impedance goes down. Or up as the square. V squared, V over I. So so
this was one of the first, I don't know, question that I've been through, and I don't know why I got it the other way around. So
yeah, well,
because there's a 40 volts between the answers, and I thought if you reverse the calculation, 40 would be the right one.
Well,
but now I can't remember exactly why I got this.
If you flip it around and you have 1500 turns here,
yes,
and 500 turns here, and you have 120 volts, then you'll have 40 volts over here. Because then you have 3 to 1 is equal to 120 over 40. So you'll have 40 volts. That's a step down transformer.
I have to check on the app. It might be the anyway. Okay, thank you very much for the explanation. I'll go back to that later. Thank you.
Not letting me even start before hitting me with questions, which is
I was out of the time. I mean, it's
I don't mind.
2 minutes too. So
well, it's already dinner time. Well, you don't eat dinner until 9 at night, right? 2100.
Yeah, it depends if you are on the north, on the south. Yeah, on the south is like you are saying it's more or less 9 o'clock. But for me,
2100.
Yeah. But for me, dinner is already gone. So I'm here till I don't know midnight or whatever it will be.
It is 9 in the morning over here. So
it's 6 o'clock.
Yep.
PM.
PM.
Yeah.
Giovanni, where are you from?
Italy.
Where in Italy?
Northwest. Close to transport.
Oh, my wife is from Sardinia.
Whoa! Oh, very nice place. IS0.
It is. It's a separate.
Her call sign would be.
It counts as a separate DXCC country.
Yes, absolutely. Yes. I don't know why, but that's how it is.
It's separated by a distance. I don't know. So is Corsica. So.
Well, I'm from Sicily, and we are not separated at all.
Yeah. Well,
don't ask me why Sardinia got this special treatment.
Yeah, that's true. There's a lot of rules like that, like Saint Pierre and Miquelon. St. Paul Island is considered separate from Canada. Oh.
Right.
St. Pierre and
Well, Saint Pierre
Miquelon
and Miquelon is
because it's
French.
French. That's right, because it's French.
Well,
Oh,
you have more or
can
less.
I?
You have more or less the same rules because I learned about the 48 continuous states. So if you calling CQDX, you're actually calling to someone outside the 48 continuous states, which would be Alaska, Hawaii, and don't know, Puerto Rico, maybe.
Yeah. Basically off of the continent, we'll
Puerto
say.
Rico.
Puerto Rico.
Yeah, might be Sardinia
Virgin
might be
Islands.
considered more or less the same, so it's off the continent. So
Yeah, the
it's a
times that
different
I've operated,
country.
the times that I've operated in Italy, basically, if you're calling CQDX, it means outside of Europe. So,
Scott, can I make a quick comment?
sure.
Sure.
So yesterday, here in Canada, our tests are a bit different. It's one test,
It
and
is.
if we get 70%, we get what's your technical license, and if you get 80% more, you get what's your general license.
Just so you
And
know,
just for the fun of it,
just so you know, I have the basic with honors and the advanced license in Canada too.
oh wow,
So I can
you
speak
lived
to
in
that.
Canada then?
I worked in Canada quite a bit.
Oh, nice, nice.
So,
In any case, I just wanted to say thank you. Yesterday, I took the practice test, and I have at least 8 questions that I got right because of your course.
and by the way, it's funny. The advanced exam in Canada is actually, for me, I thought it was easier than the basic because it's all technical. It's not rules.
Yeah, the Canadian, to get the Canadian license is much more on the technical side from what I've read.
Now the
That's why I
basic
wanted to take your management course here.
the
General.
basic test, the basic license, it's 100 questions. I mean, it takes a lot of work. It's 100 questions long. So, and the
Brutal is
question,
what I use.
yeah, the question pool is 1,000 questions, and I studied for it for about 3 months, off and on, just to do it. So I'm Victor Alpha 7 November Juliet India, and the RAC Canada. Yeah, somebody does have a pretty bad echo, but I don't know who it is. That's why headphones are always good.
VA, so you were in BC, Alberta or something?
Yeah, I was working in British Columbia, and the company that I worked for has an office in BC. So, um, yeah, yeah. So yesterday, last night at 4 o'clock, started the RAC Canada Winter Contest. So I did that for about 4 hours last night. That was a lot of fun. It's still going
Oh, you
now.
were on that. I watched it for a little while.
Yeah.
It broadcasted live.
I'm running QRP, which is 5 watts with dipoles, and I'm up to about 60 contacts right now. And obviously, I'm not on right now. But if we were to go to a web SDR, for instance, in Utah, that one, we would see that there is a lot of activity going on right now for that, and which I am missing, but that's okay. I'd much rather get all of you to the point where you're on the air on HF being able to do this stuff if you're not already, then get to work another one. And besides, if we end at 1 o'clock today, then I still have 3 hours before it's over. So,
Well, can't you use everybody that's on today because they have call signs as a contact?
no, it has to be on the high frequency bands. Sorry. But we were looking yesterday at let me share this a little bit. Whoop. Okay, everybody, this is a good test. Can everybody have audio?
Yes.
Yes.
Okay, well. A lot of activity today.
Gee, they're fast. Do you think that those are pre-recorded?
What? AA7V?
The Morse code introduction?
No.
No.
I mean, they could be. I mean, I'll sometimes program it into a keyer or something, but I could certainly send it by hand.
Oh, I see. Declare yourself. I guess.
No, most CW operators are real. They don't.
Yeah.
I'm
Anyway,
asking. I'm brand new to this, but this is what I want to do. The little radio QRP that I bought has some pre-recording that you can do, so you can do your call sign and CQ, and then you just broadcast that instead of keying it.
But you still need to be able to copy everything.
Yeah.
So
it's just they're so fast.
So
you know what? With a paddle, I can do 40 words a minute with a paddle. So if I can do 40 words a minute, you can do 20 words a minute with a paddle.
I think what you said yesterday about because Morse was always one of those things where I was like, no, not going to happen. But I think what you said yesterday about not having to get the whole thing, just getting the gist of it, gets you, you know what I mean? Like that made more sense to me, and it made it a little bit more attainable.
I mean, if you're in a contest, you have to have 100% of copy.
Right.
But if you're just having a conversation, you kind of do it in context. So
yeah.
But there's been studies that showed that you don't even need to have all the letters in a row. All you need is the first letter and the last letter of a word, and your brain fills in the rest.
In the blanks. Yeah, it does.
So,
yeah, it can. All right, everybody ready to get started?
Yep.
Okay, so good morning, and my call is N7JI. My name is Scott. I live in Eugene, Oregon, and I'm kind of a ham radio addict. I've done this since I was 15 years old. I just hit 40 years of licensing this past month, and about 8 years ago, I started in earnest saying, I should teach classes, and maybe it'll work and maybe it won't. And I believe this is the 45th time I've done this, either like maybe the third for general that I've done, but a whole bunch of technician classes. I hope everybody who came there yesterday found it entertaining, maybe, and hopefully informative to the point where you got something out of it. I don't typically do so many general classes because I feel like in a way I've gotten more bang for the buck as far as creating new operators by doing a technician class. But I figured for this one, it's been so long since I did it, and there are a lot of people that say, somebody should teach a general class, that I figured, okay, maybe it's time I did one again. So thank you all for participating in my experiment. And as the first part of the experiment, we're actually not going to start at page 1. We're going to basically start at page 71, which is radio wave propagation. And similar to what we did yesterday, I'm not going to start with the book. And instead, what we're going to do is do a refresher on waves and stuff like that, because I think my own kids, my wife, they don't really I don't think they have a really good understanding of what it is that radio even is or does. So I think it's beneficial to go over it, just as a as a general rule, to try to get everybody on the same page. So okay, the first thing we do. Everybody ready before we any questions before we start? Okay, nothing hurt.
Nope.
Okay.
Is that the same book that we used for the technician?
Nope. This is the general book. This is the other one that I referenced in that email that I sent out.
Okay, I missed that one. I'm gonna have to have a look at it. Thanks.
Okay. All right. So
Sorry, Scott, real quick,
basically,
will these be recorded as well?
it already is.
Okay, great.
Yep. Okay. So here we have a unit circle with a radius of 1. There are 360 degrees in a circle. As you are, let's say, sitting on a dot on the circle, we'll call this the merry-go-round. As you go around the circle, you will find that you're going in the counterclockwise direction to increase your angle. And as you spin around this circle, we're going to first look at how far up and down in this direction you go. This is also known as the y-axis. So at the point 0, we're going to start with a black line, go like this. We're going to say 0, 90. Those are the points of interest, 180, 270, and 360. Those are our angles. So going up and down at point 0, we're going to start right here. Then we get to 90 degrees. We get to a value of 1 because we're way up here. This is the positive. This is the negative. We get back down to here. Then at 270, we're at -1. And then at 360, we're here. And this map, to connect the dots with curves. Anyone know what this is called?
Sine wave.
A sine wave. Okay. So now what we're going to do is instead of that, we're going to say left and right. Where this is plus and this is minus. We're going to do the same thing, except now we start over here and we're already at 1 unit. Then at 90, we're in the center. And down here. And then we come back up here and we come here. Connect all the dots. Okay, these look very similar, don't they? And in fact, if we were to continue these off into the distance, we would see that, in fact, because circles go on forever, we can always keep spinning around that circle. We would find that these actually are just little snapshots of the exact same thing. The only difference is that this is the sine wave.
Out of phase.
And this is the cosine wave. Is that the cosine is 90 degrees ahead of the sine, which makes sense because, well, we're starting 90 degrees off. It's really basically one is just 90 degrees shifted from the other one. So actually, I did that wrong because it's early and I'm still making mistakes. This is the sine. And this is the cosine. There we go. So the cosine wave is 90 degrees ahead of the sine wave. We can look at this and say, okay, here's our 90-degree distance. The cosine peaks 90 degrees before the sine wave does. Okay, so now while this is happening, we can take a look at these waves and some things that we can change with regard to these waves. Well, each of these is 360 degrees from peak to peak. In other words, to go 1 full time around the circle is 360 degrees. And what we're going to do is I'm going to erase the cosine wave because it's just a special case of the sine wave, really. So the cosine wave is going to go away, and we're just going to focus on the sine wave. So there's the pink sine wave. So what we're going to do now is take a look at this sine wave, and we're going to see what's interesting about it and how we can make it more interesting. So what are some things we can do to make this sine wave different?
Increase the speed.
Increase amplitude.
Increase the speed that we're going around the circle. Well, what will that do? We still get to 360 at the same time, right?
Makes more waves?
Well, no, because we're just looking at angle. So we're going to get to that one. What's another thing we can do to this wave? We can make it so the circle is... Yeah, we can make it so the circle's bigger. And then, instead of getting up to 1, it gets up to 2. That is
Amplitude.
called amplitude. Yes, we're changing the amplitude of the wave. Okay. And what's another thing we can do? We can change where we start. Yeah. Well, we haven't increased frequency because we haven't done that yet. So we can change where it starts. What's that called?
Phase shifting.
Right. We're changing the phase. We're starting it at a different angle position on that circle. So by doing that, we can alter the position of that graph. Okay, now what we're going to do is we're going to change that unit on the x-axis here, which is in angles. We're going to make that time. Because now we not only are looking at just what the circle is doing, but now we're going to say that it's moving around at a certain speed. So now we're going to do this, get rid of this and redraw it. It's very colorful. Okay, here we go. We're going to redraw the circle in a totally different color. All right. It still has 360 degrees, so 0 and 360. And we are now going to say that we spin around this circle as we go this way. Our angle increases. We usually use the Greek letter theta for the angle. And now what we're going to say is we have a certain amount of time in which that happens. So what we're going to do now with it is say that we're going to give it a base unit of 1 second to spin around. So how long would it take time-wise to map out that picture?
3 minutes.
1 second, right? We said we go around every 1 second. So this goes from 0 seconds to 1 second. Okay, what if we increase the speed that we were going by a factor of 2? How long would it take to go around the circle?
Half.
It would take a half of it. Okay, so as we do that, what we would see is that our sine wave would do this.
Closer.
I need to fix that. I don't like the way that came out. All right, one more time. There we go. Okay, so we shortened it so that it now takes only a half of a second to make that total circle. And now we have 2 of them in that 1 second. Okay, so what happens if we instead make it so that we're going 10 times as fast as the original speed? How long does it take to go around that circle?
1/10 of a second.
1/10 of a second, which means that in 1 second, we now are at the point where we have made 10 pictures that look like that. And for the sake of argument, I'm just going to draw one of them because otherwise it gets really crowded. Right, and we'd have 10 of them in that period. Okay, the time that it takes to go around in seconds is known as the period. And the number of times that we go around in 1 second is known as the frequency. And that's equal to 1 divided by the period. So if our period is in seconds, what is our units of frequency? 1 divided by seconds. Or if you want to think of it this way, things that happen per second. Or, as we used to call it, a cycle per second. Because a sine wave is 1 complete cycle of a wave. This has a name. This is called a hertz, named after Heinrich Hertz. So we have that time, or our period, is equal to 1 over the frequency, and vice versa. Okay. So now what we're going to do is say, what else can we do with the sine wave now? And it was mentioned before. We can do this. Here's our original sine wave. We can change the amplitude. by changing the size of the circle. We can change the phase by starting it at a different point and ending at a different point. And now what else can we change?
Frequency.
Frequency. Okay, these are all interesting things that we can do with this particular wave. So now what we're going to do is we're going to take this thing and turn it on its side. So we're going to take that original circle that we had and rotate it. So our circle looks like this. Think of this as a bicycle wheel. And as we rotate it, it will start to look more like this. And if we rotate it further, it will start to look more like this. If we keep going, it will eventually just look like this. So we go from a circle to now, what do we have?
Line.
An up and down line. Okay. Well, it doesn't mean that we're not actually on the circle, right? I mean, we're still going for a ride around the circle, and it still has a frequency and it still has a period, except now we see it as going like this. And in the extreme, what we get is we just see a dot that is moving up and then coming to a stop and then moving down and coming to a stop and then going back up and coming to a stop and moving down like that. It's just going to look like a vertical dot moving up and down. Okay, so as that's happening, where is its speed going to be the highest?
Middle?
Top and the
Right
bottom.
in the middle, right in the center, where it's right in the middle of moving up and down. Okay, so now what we have is a line that is just up and down, up and down, up and down, but it doesn't spend the exact same amount of time in every place. So we're going to draw that. Here's our line. But we really have something that's moving up and down and up and down and up and down in the form of a sine wave. Okay. Well, what we're going to do now is stretch this out because, you can do that, but it's kind of boring. So we're going to add another third dimension to this. And this is the third dimension.
Time.
We're going to move it at a velocity v. We're going to take the bicycle wheel, which has the thing that's moving up and down with a frequency and a period. These are both happening, but now we're also going to add this velocity. Okay, so what we now have is we have something that has a frequency. And what are the units of frequency again?
Hertz.
Right. So, but in this case, it's hertz, but we really need to think of it as dimensional units, cycles per second. That's what hertz are. How is velocity measured?
Miles per hour.
Miles per hour, or how about per second? The most common way to do it in the meters, kilograms, seconds unit is meters per second. Okay, so now we have something that is going up and down with a frequency in cycles per second, which we don't know what it is. We're just going to give it we're just going to say that it's 1 for the sake of argument. And it's moving to the right with a velocity of meters per second, some meters per second. So as we were to do this going up and down is now stretched to the right. And it looks like that. And because it's in 3 dimensions, it's actually stretched out in the form of a helix. It actually makes a spiral. But we're only kind of looking at it from the side here. So as it's moving off to the side, it carves out a path in space. So if we want to know, we can arbitrarily say that we want to know how long it takes in distance to make one cycle. Make a picture of one cycle. This is a cycle, one full wave. That's a cycle. We can just say, okay, well, we're going to create this new thing. We're going to say that this thing that we created, and we're going to arbitrarily divide one thing by another. We're going to divide velocity by frequency and see what we get. Because in math, you can do that. You can do anything you want. It's math. We now have the units of meters per second divided by cycles per second. Well, because we have divided by per second, we have multiplied by per second or divided by seconds, we can just actually cancel these. So now we have a new unit, which is meters per cycle. Okay, now we look up here and we see, what is a cycle, everyone? What is that a picture of?
Portion of the wave.
Portion of the wave. That's a wave. That's a wave. That's a wave. That is one wave. And what do we now have associated with that one wave?
The wave.
We have a length in meters. We have a distance. So this is obviously called a wavelength because that makes sense. We use the Greek letter lambda for wavelength is equal to velocity divided by frequency. And this is in meters per sec. And this is in hertz. And this ends up being in meters. So now what we have is a velocity that something is moving, a frequency that that cycle is going around and around on that bicycle wheel, and that tells us how long the wave is physically in space as the bike wheel is moving to the side. And if you want, you could actually go get a bike wheel and spin it and put an LED on it and walk to the side and use a like, you know, a video camera or something and actually see that it makes a sine wave picture. It actually works. If you walk faster, your velocity goes up. What happens to the wavelength that's carved out? If the velocity up top gets bigger, the wavelength gets longer. If your frequency increases, your wavelength gets shorter. Well, this is kind of what we already know to be true, because if we look at, let's say, 440 hertz. In music, this is a tuning A. We use that as a tuning note. Well, we have a velocity of about 330 meters per second for sound. Okay, so this is an A note, is 440 hertz. This is the speed of sound in meters per second, and we can say that wavelength, lambda, is equal to 330 divided by 440 is 0.75 meters. So for a longitudinal wave, like a sound wave, at 330 meters per second, which is basically the speed of sound at sea level, this makes a wave which is in space, in air, 0.75 meters long, because it's traveling through air. So now we're going to take the next big step. We're going to take a look at a different kind of wave. And this different kind of wave is generated by the same thing, which is something going around in a circle, moving up and down as you see it from the side, moving in this direction. This is an electron moving back and forth. An electron is a fundamental particle of physics. It is an electric charge. As it moves back and forth, it actually creates a magnetic field and an electric field. And so we're going to make the electric field go in this direction. This is our plus and minus. And we're going to make our magnetic field up and down like this. And we're going to move the wave this way. As that happens, what we get is an electric field that now propagates this way, perpendicular to the magnetic field, which goes like this. And if you were to look at it, it's basically perpendicular to each other, and they're perpendicular to the direction of movement of the energy generated by the wave. To understand this and how they are related, if you use your right hand and you stick out your thumb and you stick out your index finger, these are right at right angles to each other. You then use your middle finger. The thumb is your electric field. Your index finger is your magnetic field, and your middle finger is the direction of movement. So we call that letter S. We call this electric field E, and we call this the H or B field for the magnetic field. I should change the color of that. So the S vector is the direction of movement of the energy that is then created and travels through space. It turns out that the velocity that this travels at is 300 million meters per second. Does anyone recognize that number?
Recognize that number? Speed of light.
Speed of light.
Speed of
Okay.
light.
Okay. So as this energy being generated by a moving electron, an oscillating electron, goes up and down, moves out in the direction to the right, it's traveling at the speed of light. So we can say, okay, the speed at which, or the frequency at which the electron is moving back and forth that's making it is somehow combined with the speed of light to generate a wavelength. The formula still works. But since that's the speed of light, we can get rid of the letter V. We can use the letter C for the speed of light. And we can say, just like we did before, that lambda, which is the wavelength, is equal to the speed of light divided by the frequency that the electron's moving up and down and making it. Well, okay, so let's do an actual sample. So let's say that our frequency is 1 hertz. 300 million divided by 1, which is
300 million.
Right, or 300,000 kilometers, right, which is pretty close to the distance from the Earth to the moon. It's a pretty long wave, right? That would mean that from peak to peak, from here to here, that would be 300 million meters. Well, okay, that's kind of long. So we're going to do something else. We're going to change that up, and we're going to try to make this something that we can actually use and understand. And so instead, let's go with 1,000 hertz. And now we're going to have lambda is equal to C divided by F again. It's 300 million divided by 1,000. Well, we're going to cross out 3 zeros. And our new wavelength is 300,000 meters, which is about 300 kilometers. Okay, well, that's still pretty far. That's almost 200 miles. Still kind of big. So now we're going to take away 3 more zeros here. We're going to say our frequency is
Hertz.
1 megahertz.
1 million hertz. So our wavelength is now 300 million divided by 1 million. Cross out 6 zeros is 300 meters. That's about 1,000 feet. But our frequency is now 1 million times per second that the thing is moving up and down and making this disturbance. Well, we have 6 zeros. That's 10 to the 6th power. We represent that with the big letter M. Now we have frequency of 1 megahertz. So 1 megahertz makes a wavelength of 300 meters. Well, we can keep going with this. We can say that we have a frequency equal to 1,000,000,000,000,000,000,000,000, right? In hertz. We could make this even longer, right? That I believe is 1 terahertz, is it not? Times 10 to the 12.
Yep.
So lambda is equal to 300 million divided by 1,000,000,000,000,000,000,000. Cross out this one, cross out this one.
0,0003.
Yeah, 0.0003 meters. That's pretty tiny, right? That's 3/10 of a millimeter. And we can keep going with this. All of these things are just electromagnetic waves because they have an electrical component and a magnetic component. But notice that if I change the frequency to all these different things, I can make all these different wavelengths. So it is important to understand that by simply changing the frequency and changing the wavelength, I can make all kinds of different stuff. Now I bring this up. Okay, so as I do this, what do we end up doing? What happens if I make the waves even shorter to the point where they're in the nanometers or billionths of a meter long? What do I get?
Light.
I get light. How about if I shrink them even more and I get to 100 nanometers? I'm at a boundary between what? What is UV?
Ultraviolet and X-ray.
Ultraviolet and X-rays. If I make them a little bit longer, go to 1 micron, I'm at infrared. And if I go to 1 millimeter, that's a boundary between infrared and microwaves. Microwaves are a very, very short wavelength form of radio. So what does that really mean? This is our electromagnetic spectrum. And how are radio waves similar to and different from good old Roy G. Biv that we know as the colors?
Difference.
What's the difference between them?
Their frequency.
Their frequency and their wavelength. It turns out as you move to the right, it also is related to the energy of the photon carrying the energy. So radio waves are very low energy photons. Infrared is higher energy. Colored light is a little bit higher. Ultraviolet is even higher. X-rays are even higher. And then there's cosmic rays and gamma rays. And those are way up in the very energetic part of the spectrum. So is there an actual end to this in either left or right directions?
No.
Well, to the left there is. You have 0. You can get down to 0 hertz. Yeah, you can get down to 0. How about to the right?
Unknown.
frequency, yeah, you can increase to infinity, which makes the wavelength basically zero, right? There, but since we don't really know what happens at that point, practically speaking, we're just going to focus on the fact that we have 6 colors or 7 colors that we can recognize, and ultraviolet, infrared, and X-rays. So the question then becomes, why is it that we see red as red? Why is that different than
Cones
blue?
in our eyes.
Yeah, our eyes can differentiate very, very fine changes in color. Wavelengths of different light trigger different sensors, RGB sensors in our eyes. They're called cones, and cause us to see different colors. 660 nanometers is very red. 500 nanometers, if I remember right, or 540 is very green. About 480, 500 is very blue. 450 is very purple. And everywhere in between triggers those different receptors to the point where we see them as different things. So why don't we see infrared?
Because it's below the frequency.
What was the movie where I can't remember the name of the movie. What was the movie where the creature could see people's heat signatures?
Predator.
What was it?
Predator.
Predator. Thank you. Yes, Predator could see infrared. Predator could could pick out people in the dark. How about ultraviolet? Birds and bees, because certain flowers and things that they look for have very, very strong emissions in the ultraviolet range. So they have become adapted to pick up those colors that we can't see. So we have these incredible sensors that are able to tell the difference between all these different frequencies. Well, since radio waves and light are really the same thing, what do we use to see or hear or be able to detect various different frequencies really well? If we're looking at infrared, we have an infrared camera that picks out different heat signatures and gives them different colors falsely so that we actually know what's there. Well, for radio, we need a detector to detect radio waves. Fortunately, we have one of those. And it looks like this. So what we're looking at, this spectrum, this tiny little piece of that entire spectrum, is everything that is happening that we can detect right now between 28.020 roughly and 28.040 megahertz, which relates to those particular wavelengths. And our system that has been built in this particular case is basically able to pick out these slightly different colors of light, if you want to think of it that way, be able to display them visually in false color, which is what we're seeing. I mean, doesn't really paint a picture, but it's turning something that is floating around in space that we can't see or hear and putting it on a screen so we can see where it is. And not only that, once we know that it's there, we are able to convert what's there into sound, which we can listen to. That is basically the whole purpose of radio. That is what radios do. So we could, for instance, do this. So realistically, what is happening in this case to make that thing even be there? We're taking a color of light and we're stretching it out and we're adding different information to it to make it carry that information for our benefit, because we know that somebody on the other end will be able to listen to it if they can do the reverse. That process is called modulation, and that's what radio is. That is the fundamental use of radio. That is basically taking electromagnetic waves and putting information on them through the process of modulation to make them be able to carry information from point to point. We can do the same thing with light. It's actually very likely that we are actually talking over light right now. Everybody, did anyone know that?
Makes sense.
In what form?
Fiber optics.
Fiber optic cable. That's right. And the higher the frequency, the more you can put information on it, the more information you can place on it, which is why fiber optic cables are very good at very high rates of information, such as being able to encode everybody's video on my screen at the same time where I can see everyone and hear everyone, and everyone can hear me and see me. All right. So now that we've gone through where electromagnetic waves come from and how they are formed and how they basically come to exist, what we're going to do is we're going to share my screen here, and we're going to start on page 71, which is known as radio wave propagation. The assumption is that everybody at this point has a basic understanding of what radio waves are, why they exist, how they exist. And now what we're going to do, because this is a general class, is get into stuff that that general class operators are a little more acutely involved with than technician class operators. The reason being that everybody should have received this, which is the medium frequency, high frequency, very high frequency, ultra high frequency band plans. I should have sent this to everyone. And you will note that all the way on the right-hand side of this, there is no indication of what operators can use certain frequencies up here in the VHF, UHF, and that's because anyone with a technician class license or higher can use those frequencies at will, unless there's, unless you're like within a certain distance of the Canadian border or somebody else is already there, etc. But then when you get down into the medium frequency and high frequency band plans, what you find is that the band plan is now marked with these different letters, E, A, G, and then an asterisk. The asterisk indicates that somebody with a technician or novice class license has privileges down there. But a lot of these bands, you'll notice, like 10 to 10.150, extra, advanced, and general. This is why you're in this class, so you can get ready to pass your general exam. The general exam gives you access to all these different frequencies, 10 through, well, 160 meters, and then all the way down to 2200 meters, which I've never used, or 630, which I've also never used, but I've heard it can be interesting. What ends up happening is that because your signals are no longer largely contained locally or relatively locally, they are now at the whim of what the ionosphere is willing to give you. How the ionosphere behaves determines whether these frequencies are going to do certain things or not. So, for instance, right now, when we were just listening to this right here, okay. Anyone know what band this is?
10 meters.
10 meters, 28 megahertz, right? The fact that we hear anything on this band right now is really quite a miracle, because for the past 9 years, up until about the beginning of 2024, that band was dead almost all the time. For the last year or so, it has been absolutely rocking. Part of this, part of learning for the general exam is understanding the stuff that happens that makes the high frequency bands really interesting, because that's the largest part that gets added by your license. So the first thing we do for this is we draw the Earth, And we're going to draw our atmosphere. And up here, we're going to put the sun. Okay, so what comes out of the sun? Let's everybody name some things that come out of the sun.
Ultraviolet rays.
Okay, we've got particles.
X-rays.
X-rays. I heard ultraviolet.
UV rays.
What else? Yep. I hope we have light. What else?
Heat.
We have heat, which is infrared.
In a sense, color.
Yep, that counts as light. And we have radio. We have radio waves. And we've got a lot of neutrinos, which we can't really deal with very much. They don't interact with much. So basically, the sun is continually bombarding Earth with lots and lots of things. The two main ones that we're going to focus on are X-rays and ultraviolet. So the difference between radio waves and light and infrared and X-rays and ultraviolet is that as we look at our spectrum, we find that at the low end of the energy spectrum is radio. At the high end of the energy spectrum are ultraviolet and X-rays. This is increasing energy. Radio waves, very low energy. X-rays and ultraviolet, very high energy. So for those of you who are here, I'll bet you didn't think that we were going to be doing a quantum mechanics class today, but we have to in order to understand this. So here is an atom, and we're going to say that this is an oxygen atom. Okay, this has 8 protons, 8 neutrons, 8 electrons. The electrons that float around inside this oxygen atom, they orbit, or they have, I guess, energy states. We have 2 at the bottom layer, and then we have 6 that are moving around in a different energy level. What happens is that what happens here is that you basically have to create enough energy differential to take one of these electrons and cause it to completely be ripped out of that atom. Light, infrared, radio, they don't have enough energy to do this. X-rays and ultraviolet, those photons, which are a particle version of a wave, have enough energy to transfer to an electron that they can actually make it so energetic that it flies right out of the atom. This happens a lot of times. So what you end up with is in the upper atmosphere, you end up with oxygen atoms, sometimes nitrogen atoms too, which are now positively charged because they're missing an electron, and electrons, which are now floating around. At the same time, we down on Earth launch these things called electromagnetic waves. And that is in the form, in our case, of radio. When we do that, our radio waves, depending on how many electrons are up here, what the density looks like, so these radio waves, which we then send up, encounter this area of electrons. Well, electrons, as they're moving around, they create currents, they create magnetic fields. Well, that interacts with some of the radio waves that we send up. Some of them can transfer their energy, and the end effect is that our signal on some frequencies, some wavelengths, can actually, depending on the density of the electrons, be refracted back down. Sometimes depending on the frequency, they just pass right through. Sometimes, depending on the frequency and the wavelength, there is a very high density of electrons and ions way down here that will take radio waves and basically absorb them, and they go no further. It basically is so dense that they'll catch all the radio wave energy that we're sending up, and it will be dissipated as heat. And but what we end up seeing at that point is absorption. So these different layers of the ionosphere are called the D layer, the E layer, the F1, and the F2 layer. The D layer starts at about 50 miles up. The F2 layer goes up to about 600 miles up. What we end up with is sometimes some of these waves will get up to the D layer and bounce around. Typically, up at the highest levels in the F layer, the more dense the electron clouds up there, the higher the frequency that they will be able to refract back down. So this gets back to the question, okay, so 10 years ago, over the last 10 years, this is what our Earth looked like for 10 meters. So there's the Earth, here's our atmosphere, D, E, F1, F2. Ten-meter waves are launched up to space, and they do this. Over the last year, our 10-meter waves would go like this. The reason for that is that obviously something is different. What's different is that if anybody noticed that we had a beautiful aurora back in May, that was evidence of the sun being very, very active. When the sun gets active, it tends to spit out a higher rate of X-rays and ultraviolet toward the Earth. That causes more ionization, and it causes, instead of light clouds, it causes really dense clouds to form. The higher the frequency, or the higher the density, the higher the frequency can be that can be bounced. So what happens is this is called the maximum usable frequency. The sunspot cycle is 11 years long, roughly, and that's been observed experimentally for about 400 years. So every 11 years, the sun goes through periods where its radiation goes up and radiation goes down. And this is ionizing radiation that causes ions and electrons to form way up in the sky. So we have something called our maximum usable frequency. We also have something called the lowest usable frequency. And what happens there is that at the same time, this D layer builds up when the sun is right overhead, and that causes our lowest usable frequency to basically trap radio waves down at the bottom level and not let them through. So we end up with a window between the two where we have maximum and lowest where things will actually work. When we get a really, really big solar storm, what can happen is we can have a lot of X-rays that build up this layer really thick, and the lowest usable frequency increases to the point where it's actually where it's actually above the maximum. And we call that a radio blackout. And that's why when we have like a big X-ray burst for a couple of hours, we can have a complete radio blackout. There's tons of noise being made, and there's tons of ions and electrons being separated from each other at low levels. Now, what happens at night is that all of this kind of dissipates because we don't have any more solar radiation coming in because it's nighttime. The sun is on the other side of the Earth. This D layer disappears. The lowest usable frequency drops a lot, and we can use our very low frequencies. What ends up happening also is that a lot of these electrons find other atoms to combine with, and the density drops off, and our maximum usable frequency goes down. This is why we have daytime bands and nighttime bands. And this is why we have bands that work really well at the peak of the sunspot cycle and bands that actually work better at the bottom part of the sunspot cycle. And why seasonal variation makes a difference between summer and winter in your hemisphere. During the summer, our summer in the northern hemisphere, the North Pole is essentially irradiated with solar radiation all the time. That makes it a pretty good path to get to Europe on the higher frequencies. But during the winter, it's dark all the time. So that kind of shuts down that path to a large degree. However, you could go around the South Pole because it's sunny, and it turns out that salt water, being a really good conductor, is a very good surface for bouncing radio waves off of. And when you take a look at the path between, let's say, the West Coast and India, over Antarctica, it's mostly salt water, except for Antarctica. So even though it's 17 miles longer or 17 miles long of a path instead of 7,000 miles, it's actually a more favorable path. So the long path is actually easier to work than the short path. All right. Any questions before we go over the book? And I
do have a question right quick. So
yeah,
you're talking about the 10 meters being active. So is that because we're at the beginning of that cycle or in the middle of the cycle?
We're
so will 10 top. Stay active?
We're at the top.
Okay. So it got better for a while. Now it's going to start degrading again.
And it's going to start degrading. Yeah.
Okay. Thank you.
How long is it going to take?
It'll probably take a couple of years before it really starts to go downhill.
All right. So we have time.
We have time. Yeah.
Okay.
Other questions? What band is more active when the sunspot cycle is not peaking? All right. So 20 meters is when we're at the bottom, right? And if you've been through a solar minimum, man, it's rough. You basically, your world ends at, let me share that thing again. There we go. Your world ends at 20 meters most of the time. 20 meters is kind of like a superhighway. It's essentially always there. During the daytime, 20 meters is always going to be good. Right now, 20 meters is actually okay because all these other higher bands are better. But at the bottom part of the sunspot cycle, you'll still be able to talk to people on 20 meters anywhere all the time, depending on the time of day and stuff like that. But yeah, there are, long stretches of time where you don't hear anything on 10 meters except locals. And 15 meters might open for a half an hour to somewhere, maybe. But then because you have, everyone knows that these bands are going to basically be dead, 10, 12, 15, and 17, with a few exceptions. You have a very high concentration of people who are operating down on these lower bands. So that, that's a saving grace. It basically means time to put up bigger antennas because lower frequencies require bigger antennas.
Scott?
Yep.
I remember at some point along the way hearing that 40 meters is best in the day and 80 meters is best at night, and that's essentially related to the ionization due to the sun peak wherever that's falling across the planet.
I don't know about 40. I mean, 40 and 80 are similar. I mean, 80 is definitely a nighttime band. 40 is usually okay for local communications during the daytime, but it really opens up at night. You'll get 40 meters going long sometimes, and you'll get, coast to coast or worldwide communications on 40. But
Thanks.
I mean, just because it's a higher frequency, but it's still one of the low bands and it behaves that way.
Okay.
It's a nighttime band. And I mean, one of the things that one of the cool things that we can do is um, let me shut that and go here. And I'm gonna take a moment and open up a website called PSK Reporter. Has anyone been on FT8? Has anyone used FT8?
I've tried it on 2 meter. Of course, I just have my technician license as of now, so
Yeah.
I just briefly tried it with a local general just to kind of get a taste of it.
Okay. So FT8, because it's a very low power mode that allows you to do a lot of a worldwide experimentation with very low power or high power. What it will do for you, because it's a computer-based mode, is that the software that runs it can be told to report all your contacts to this big internet server. The big internet server basically looks at all those contacts that are being made and combines them with the location of the other station, reports all the information, and puts it on a map. So you can take a look at, from any particular place, what bands are working to what places. And okay, so we're basically looking from either northern Germany or southern Finland or southern Norway. What do you notice about the map going east and west? Over here on the right-hand side, they're all blue. That's 40 meters. Over here on the left-hand side, that is largely 10 meters, 15 meters, 12 meters. Why? What do you see?
It's daytime.
Daylight.
Remembering that the sun is moving to the left on this screen, which means that it was just recently daytime in Europe. It's now nighttime, right, Giovanni? Right, Joe? So what that
Yeah,
means
that's
is
right. Sorry,
it's
I was
yeah.
browsing around. Sorry.
So basically, as the sun is moving west, what's happening is that all these regions farther east, like all the way to China, Japan, Southeast Asia, India, they have not had sunlight in quite a while. So that path, there's been a lot of dissipation of of the F layer electron clouds over the last several hours. So those clouds that are forming over, let's say, central Russia, Kazakhstan, are not sufficiently dense enough to carry really high frequencies. The only ones that are working are 40 meters. At nighttime, that makes sense. Looking over to the left, however, which is looking to where the sun has recently been shining, there's a lot of residual electrons still floating around in the upper atmosphere. The density of the clouds is a lot higher, and those bands, those really high bands, can still be propagated from Europe to the United States to South America, etc. As that continues to change, if we were to take a look at this in another 2 hours, this map might look totally different. That's why this is so interesting. Other questions?
Is that map based just on FT8 modes, or
It actually aggregates a whole bunch of different modes, but I would say 95% of them, 95% of those spots are from FT8.
so
Just because,
yeah, sorry.
Question,
like,
Scott.
Yeah, go ahead.
Is that representing simplex or duplex, both, when you're looking at that map?
It's just representing who's hearing who.
Okay.
So basically, if I were to look at an FT8 screen, I don't even have to be transmitting. I get every 15 seconds, I get a decode period, and I can see a whole bunch of different stations that I'm decoding all at one time. And let me share if I still have it up.
So that is not for single sideband.
No, but it does, but it can do Morse code. It can do any digital mode that's out there for the most part. Okay, so notice right here, this says FT8. Can everybody see that?
Yeah.
Okay. Yeah. So this is 10 meter FT8. We're actually looking at probably 40 or 50 signals all being received and decoded at the same time. So from my location, for instance, if I had my computer and radio turned on, I would be essentially instantly giving propagation reports of who's being heard in Oregon. And then they get put on that map, which is really an incredibly powerful tool if you think about it. Because you can in real time, for instance, I can send out one CQ and say CQ using FT8, and everybody who can hear me, if they're connected to this, if they happen to be listening and are connected to the server, will within about 1 minute report who they heard, and I will see a complete map of everybody everywhere that heard me. That can tell me what the propagation looks like. That can tell me how my antenna's doing. Try out a new antenna. If it's directional to Europe, I should see a lot of signals in Europe versus other places. If I see that, I know what my propagation, I know what my pattern of my antenna looks like. Other questions?
Yeah, so that FT8, so you're basically your radio is connected to software on your computer and somebody, the receiving entities are in the similar situation, and that's happening automatically
in real time
without the receiving stations aren't doing anything themselves. It's a
Correct.
passive. Okay.
Yeah. I mean, it can be active too. I mean, you can make
Right.
contacts as well, but like I leave my radio on during the day and it's always providing propagation reports for anyone who is looking.
Fascinating.
So it's really an amazing tool.
How do they build that map?
Hmm?
Just how do they build that map? Is just because of beacons, or I don't know.
So basically, like a signal that I send out, let's say I receive somebody. Let me stop sharing. All right. So here's the typical information that it'll be. This is typically what you'll see. That's it. Or and I'll have another one, CQ, K7, ABW, DN40 or DM43. All right, these are grid squares.
Yeah, but that is F8, FT8.
Correct.
As far as I understand.
Right. So basically then I have here a grid square map. Okay, so the whole world is broken up into grid squares. There are 32,400 grid squares. So we can now look at this and say, okay, I heard CQ from somebody in DM43. Okay, that's Phoenix. The other one was in CN87. That's Seattle. The software will then report those knowing that I am located in CN84 because that's how I configured my software. And it uses that to generate this map.
So that map cannot be generated with an SSB mode.
No.
All right. Okay.
So let's see if I look at CN87, for instance. Take a look what's happening in Seattle today. Hopefully it doesn't take very long. Now, the other thing that can be done is that there are spotting networks Whoa, look at that. And that's from Seattle. Notice the big opening to South America on 10 meters.
Oh,
Not altogether surprising considering the sun is somewhere down here right now. Over the
bigger towards us in Europe.
Yeah. Actually, yeah, quite a decent opening to Europe. I would, if I were on right now, I would probably be looking for Europe.
Bigger chance.
Yeah. Well, you gotta strike while the iron is hot, as they say. Okay. So here we go. Radio wave propagation. Now that we've discussed that stuff, we're going to start moving through the book. We should cut through it like butter because we've already covered a lot of stuff. Okay. So higher sunspot numbers. Sunspot numbers generate ionizing radiation. They are indicative of ionizing radiation. So high sunspot numbers will typically create, they are an indicator of good propagation at higher frequencies. Solar flux, this is measured at 2800 megahertz or 10.7 centimeters. The solar flux is also another measure of HF propagation. The higher the solar flux, the higher the the better the high band propagation. Okay, 20 meters. 20 meters is kind of like your super highway. 20 meters is always good. During periods of low solar activity, 15, 12, and 10 meters will basically be dead as a rock for most of the day. Okay, we have the sun rotating around its axis. Sunspots and stuff are carried by the sun's surface. The sun rotates in about 26 to 28 days. So it points at us. If we have a big sunspot or something that's spitting X-rays, then it'll affect us every 26 to 28 days. A sudden ionospheric disturbance will disrupt lower frequencies. What ends up happening again is if we have a sudden ionospheric disturbance, that will cause the enhancement of the D layer. That will raise the lowest usable frequency to the point where those low frequencies really get hammered badly. It takes 8 minutes for electromagnetic radiation to make the trip from the sun to the earth. So how do we know that there is an X-ray flare coming? Come on, everybody. How do we know?
Visually, you can see it.
No, we don't. We can't, because how fast would our sensors be able to tell us that there's something coming?
8 minutes.
8 minutes. Yeah. So basically, if it happens, we know that it happened, past tense. We know when there's a coronal mass ejection coming because that travels a lot slower. That's 20 to 40 hours. But an X-ray flare, we know that it happened, past tense, because we can see the evidence, past tense. If you've ever been on the air when one happened, you know it. Everything disappears. I've heard it once, and basically it went from lots of signals to nothing, absolutely nothing.
And lasts about how long?
Couple hours.
Oh, okay. Thank you.
Yeah. Long distance radio communication, HF from solar coronal holes. HF communication is disturbed. A coronal mass ejection often takes between 15 hours and a few days to get here. All right, a geomagnetic storm. This is something that happens when the Earth is bombarded by particles from the sun. And what happens is that those particles tend to, because they have mass and they have energy, they tend to shake the atmosphere. When they shake the atmosphere, they make things move around. Moving around makes noise. And what ends up happening is that you get a lot of noise, and at high latitudes, you get to the point where there's nothing to hear. There are two indices that we look at for this. One is called the K index and one is the A index. The K index is the short-term stability of the geomagnetic field. The K index is recorded over a 3-hour period. The A index is the overall long-term stability of the geomagnetic field recorded over the past 24 hours. Alain, you had a
Yes,
comment?
sir.
Yeah, you had a comment?
I just had a quick comment, which was you see for the Canadian lower exam, the question that was just before G3A03 that you had on your screen a minute ago, that is in our lower exam.
Yep. Well, radio is radio. The only thing that changes are rules and regs.
Yeah, it's fun. I'm enjoying it.
Okay, so MUF, maximum usable frequency. LUF is lowest usable frequency. The maximum usable frequency is path, distance, and location, time of day, solar radiation, ionospheric disturbances. And what happens to frequencies below the MUF and above the LUF? They make it through. The LUF basically determines, or lowest usable frequency, what makes it up into the upper layers, and the MUF determines what gets bounced back down. So if those are above and below, then you get signals that are refracted back to Earth. Frequencies below the lowest usable frequency. Has anyone ever listened to AM radio?
Yeah.
Yes.
Okay.
Yes.
AM radio is at 1 megahertz.
All the time.
Typically, the D layer during the daytime attenuates and absorbs signals of about 5 to 8 megahertz and anything below. Well, 1 megahertz is below 5 or 8 megahertz. So what happens during the day? Your AM radio signals make it up to the D layer. The solar radiation will cause that layer to get thick and the signals get absorbed, which is why AM radio is only local during the day. But at night, when that dissipates, it can bounce in from hundreds of miles away. When the lowest usable frequency exceeds the maximum usable frequency, you notice propagation over ordinary skywave is not possible over that path. You will hear nothing that you might expect to otherwise hear. If you want the longest distance skip propagation, you look at the maximum usable frequency and you go just below. And what's really nice is that we have many different frequency bands to choose from, do we not? Yeah. If you find that the MUF is at 26 megahertz, you're probably going to find that this 10-meter band doesn't work, but the 12-meter band does, and it's working really well.
Question.
Yep.
Is there a way to calculate those MUF, LUF, or is there a website that do this for us?
Typically websites, because they are usually generated from ionoson data and from looking at what the solar flux numbers are.
So it's just a math calculation.
Well, part of it is experimental, because you'll find that it doesn't always follow the rules. But sometimes it follows the rules, but sometimes it doesn't. So one of the things that can be done here is we're going to go to VOACAP, which was generated by the
yeah, I know that.
Yeah, Voice of America Capacity Project, or
yeah, it's on the Humlock.
Yeah,
this is a project. Yeah, I know what it is.
Fabulous tool. So you put in your power levels and you select your antennas and you say, okay, show me what my propagation looks like on that path. So notice the hot zones are typically going to be what works best. So if we were to look at, let's say, let's pick Italy, and we're going to go northwest Italy. Okay, so let's say that we want to talk to Joe from Eugene, Oregon. What would be the optimum time? Everyone? This is the clock around the circle.
1600 hours.
Well, it's 1700 Zulu. This is universal time.
4 o'clock.
Yeah.
So
well,
it's 5 o'clock. Yeah.
Well, it's 1700 Zulu. This is universal time. And the ring that gets us there easiest is 15 meters. depending on where you are on the planet, 1700 Zulu, you have to look at what your offset is. For Oregon, we are 8 hours behind. So 1700 Zulu would be 9 in the morning.
What you mean Zulu? It's not UTC?
It's the same thing. It's also known as Zulu time.
All right. Okay.
So 9 a.m. in Oregon, which would be 5 in the afternoon in Italy. Or 4. Let's see. Is that right? Yeah, 5 in the afternoon. So
No, we
you're
are
right
1 hour forward.
You're 1 hour forward. Okay.
Yeah.
So we're actually not, yeah, we're 9 hours apart. So yeah. No, 9 a.m. That would be 6 p.m. Yeah, that's right. So we do everything in UTC or Zulu in radio because it puts the entire planet on the same time zone. So for
Which is
instance, if we
also the
now
Greenwich Meridian
yeah,
time.
so now let's take a look at North America to South America, 10 meters. Look at that. And that's largely because the sun is a little south of the equator and it's really heating up that path. And that's where our bounce is occurring. New Zealand, same way. But notice it's a little bit later. Now, let's take a look at going around the other way. This is going the long way. Not a particularly great path, right? But now let's take a look at over the South Pole to India. That's 17,000 miles. But that actually looks almost as good as short path. The best path is not always the short one. Sometimes they can both exist.
Is VOA stand for Voice of America?
It did. Yeah, it was actually created by the government to figure out
I do remember
how to get signals
Yeah.
best around the world.
Yeah, I do remember VOA in my old times. Yeah. Very
Okay,
old.
let's see. So, use a network of automated receiving stations on the internet to see where your transmissions are being received. That's a great way to determine what real-time propagation looks like. How do you point your antenna when making a long path contact? Well, one of the things I think that I sent everybody, I hope, let me see if I sent it. Give me a second here. Okay, I sent this. Hopefully this opens. Okay, can everybody see that? This azimuthal map?
Yep.
Okay, this is a little bit different view of the world, isn't it? What this shows, this is known as an azimuthal equidistant map. And what it shows is that you have distance rings, and essentially around the edge of the circle, that's actually all one point. It wraps around. It basically shows the Earth as a flat disk. Each of the rings is 3,000 miles further away. So the furthest one is 12,000 miles. And the heading is the azimuth that you'll point your antenna. So for instance, you wouldn't think it, but from the West Coast to Italy is almost just slightly east of north. From the East Coast to Italy is almost completely is about northeast. From the United States to China is actually just slightly west of north. So, and from the US to Australia, you think Australia being in the southern hemisphere, but because the Earth is round, it's actually almost due west. So, if it's important to understand what your beam headings have to be, or what the Great Circle route is, and this also determines how airplanes fly, because they want to save fuel. This is the shortest distance between the points. If you want to work long path, you turn 180 degrees from that heading. If your signals get to a certain place by short path and long path, how fast do radio waves travel, everyone?
Speed of light.
What?
How long does it take to get completely around the Earth? It's a seventh of a second, 140 milliseconds. So if if the signals go both ways, you'll actually hear an echo. I've heard this. It sounds really cool. Uh, Lower HF frequencies during the summer. Lightning makes lots of wideband noise, and it will basically tear up 80 meters from thousands of miles away at night, which is why on field day, which we do in the summertime, 80 meters is a lot of fun, but 80 meters is also very, very noisy because of distant thunderstorms. Okay, the F2 region is the highest layer of the atmosphere of the ionosphere, so it makes the longest skips. Think of it as a mirror. Using the F2 region, you can make a skip of about 2,500 miles. The E region, because it's lower, if it happens to be dense enough to be bouncing signals, can give you a skip of about 1,200 miles. It's sporadic when this happens. That's why we call it sporadic E when that happens. The ionospheric region closest to the Earth's surface is the D region. The ionospheric region that absorbs signals below 10 megahertz is the D region. And why are 40, 60, 80, and 160 meters dead during the day for long distance? And that's because the D region absorbs signals at these frequencies. It raises the lowest usable frequency. Critical angle, if your angle gets too steep, it will cause it, instead of refracting back to Earth, it will shoot off into space. The atmosphere can't bend the signal that much. So the highest frequency, which is refracted back to Earth, is the critical angle. So if we were to draw a skip zone, now we're going to replace that view of the atmosphere with just a mirror, a rounded mirror. We have a signal that goes up and a signal that goes down. Most of the signal will end up in this area. This is called, this area in between is called the skip zone because your signal skips over it. However, you can have scatter, which has small amounts of RF energy bouncing throughout the skip zone, and that's known as scatter.
I don't get this. Can you explain it again? What's the difference between scalar and skip?
Skip is basically your signal. It represents the signal for which most of it bounces back properly. Scatter is small amounts that are refracted at weird angles.
Within the skip angle.
And so why are HF scatters in the why are HF scatter signals in the skip zone usually weak? Because only a small part of the energy is scattered into the skip zone. So it's
yeah, now I get it.
So if you're listening, let's say you're listening to somebody who's in Austria, and you can hear that person in Austria working somebody stateside, right? You can hear the stateside station, but you barely hear the signal in Austria.
Yeah, I think I got it. Yeah.
And that's because you're too close to hear each other, but you might get a little bit of scatter. Scatter is very unreliable. Signals have a fluttering sound.
Yeah. Yeah, I got it. Thank you.
Okay, NVIS, near vertical incident skywave. This is something that we will typically use during the daytime. And NVIS is where you take a signal that goes up at a very steep angle and bounces back down at a very steep angle. This is typically used for 80 and 40 meters during the daytime. What's nice about this is that using NVIS, as it's called, you can have communications within 200 miles during the day on low frequencies, and you don't get stuff from far away disturbing you. And we call that NVIS. It's used for local communications during the daytime. And for those of you who are interested in emergency communications, um, this is actually going to be very, very useful if repeaters, for instance, stop working in a zone where that had an earthquake. 80 meters is what we actually use for local communications during the daytime and at night within emergency zones that don't have repeaters working anymore, because it's a fairly reliable way of talking over a couple 100 miles. All right. Now, notice the next section is amateur radio practices. So what we're going to do now is skip back to the beginning of the book. And we're going to go to electrical principles now that we've talked about radio waves and things like that. So how about a 5-minute break, everyone?
Sounds good to me.
Yeah,
Sound good?
It works.
yeah.
All right.
Scott? Oh, okay.
Uh,
Never mind.
Time to call the pizza guy.
Do you get Domino's there?
This guy used the whiteboard on Zoom.
All right. How's everyone doing?
Great.
Are we having
Great.
fun?
Oh yeah,
Excellent.
enjoying the class. I actually technically don't need to take the class since I passed the general this morning, but I wanted to learn more. So
Yeah. And some,
Congrats.
so somebody asked whether or not this is the current study guide. This is the current study guide. It covers 2023 to 2027. So this is the right one to be doing.
Scott,
Yeah.
I don't know, this may be something to explain later, but I'm having a really hard time connecting this whole idea of, okay, I'm on the 10-meter band and the frequencies that are on the 10 meter, and then somebody will say, oh no, that frequency is on the 20 meter. I'm not making it the connection somehow.
Here it is. This is it. This is what relates the two. So what we're going to do, I'm going to draw it a little bit neater. This relates the speed of light to the wavelength, to the frequency. All right, let's have it. Well, give me the frequency you want, and we'll figure it out.
let's go with 28.350.
Okay, that's our frequency in megahertz. All
Mm-hmm.
right, so we plug that in right there. We don't know our wavelength, so we have wavelength is equal to 300 divided by 28.35, which is I don't have my calculator open. I want to be exact. 300 divided by 28.35 gives you 10.6. Okay, so our frequency bands are colloquially known by the wavelength. Our bands are colloquially known by the wavelength. So we look at this right here. We look at our frequency band plan and we see that 10 meters covers 28 to 29.7 because it is approximately 10 meters. You want to know how to learn, you want to know how to practice these? You get on the air and you know them. The more you operate, they become second nature. You know where those band edges are. You know exactly where to be. There will be no question. If it's all new, then you'll have to have a frequency chart. And fortunately, in order to learn that, there are little pocket-sized guides that look just like this. There are full-size posters that look like this. You put it on your wall, you know where to be. One interesting thing here, of course, is that you look at, let's say, the 15-meter band, and it covers 21 to 21.45. But notice we have 21.2, 21.225, 21.275, and they're separated out extra, advanced, and general. The higher the level of license you go, you can't get an advanced class now. You can only get a general and an extra, but there are still advanced licensees out there. But if you get the general class license, that means you can go 275 to 450 on phone. If you have an extra class license, you can go anywhere. So that is one reason why a lot of people will get an extra class license because there's no reason to limit yourself, right? If you have an extra class license, you can use any part of the band that you see. It's one less thing to have to know. That and the fact that you can give tests to anybody for any license class. And when you go to any other country, an extra class license translates to whatever their highest class license is. So you get a reciprocal license, you want to operate somewhere else, you can operate using their highest level of license. which is
Scott,
actually a lot of fun. Yeah.
do you have any recommendations for good web pages to learn more about NVIS?
You know, I'm gonna say if Scott is here, Scott might know more than I do. And if he doesn't know, then maybe he knows where to find it.
Scott here. I'll look it up because I don't know specifically offhand where you can. I mean, there definitely are lots of websites. I'll just do a perusal and I'll go on the chat and I'll give you a couple of URLs. How's that?
Thank you, Scott.
Great, thank you.
Okay.
Okay, so let's see. What is reactance? Okay, notice we're into electrical principles. We're at the beginning of the book. All right, so this is what I hesitate to cover during the technician class, but I really have to get into during the general class. So it's like, the reins have been taken off. So here we go. All right, so does everybody know what this thing is?
Capacitor,
That's a capacitor. How about this thing?
coil,
That's that's an inductor. And how about this one?
resistor,
Okay. All right. So we know that a resistor does not care whatever shape of the wave passing through it. A resistor is a linear thing, and it follows this: E equals IR, or depending on how you write it, V equals IR. Does everyone agree with that?
Mm-hmm.
That's Ohm's law. Okay. The other one is P is equal to I times E, which is power is equal to current times voltage. Or P is equal to IV, but I like P equals IE because it spells the word pi. I do the same circles like this: E, I, R, and P, I, E. P is power. It's measured in watts. This is I, which is current. It's measured in amps. E is measured in volts. Resistance is measured in ohms. Okay, so for a resistor, this is all very, very true. So now what we're going to do is we're going to look very briefly at what a capacitor actually is. A capacitor is two metal plates that are separated by a gap, which is filled with a dielectric, which is a material that does not conduct electricity very well. If I take this capacitor, for instance, and I hook this up to a battery, the battery has a plus and a minus terminal. Again, we're going to ignore the fact that pluses and minuses are kind of backwards, and there was a mistake made that electrons flowing in basically a current is a flow of electrons. But by convention, because people had not figured out what electrons were, they assumed, okay, well, we have this positive terminal. We're going to say the current flows that way, out of the positive. It doesn't really, but that mistake was made almost 200 years ago, and we're just going to leave it alone and assume that it is true. So we have this flow of electrons, which is going to generate positive charges accumulating on one side and negative charges accumulating on the other side. What happens is that at that point, it becomes full, and what happens to our current? It disappears because there's no more room in the capacitor. There's no more capacity. However, if we then take, for instance, and we remove the battery completely, what happens to the capacitor?
Nothing. It stays charged.
Nothing. It stays charged. That's right. So a capacitor can be used to store energy. The storage of energy actually occurs in the form of an electric field which exists in between the two plates. This is electric field energy. So a capacitor is a way to store energy in an electric field. But now what we're going to do with this capacitor is say, okay, well, we've stored energy and we have a battery again. We're going to draw this battery. A battery is a DC device. Direct current. It's always got the same voltage. All right. So now we're going to charge this up again like this, plus, 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 minus, 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 minus. And once this is charged up, we get no current. What does no current flowing into a thing make it look like? If I did not know what was here, and I just drew this battery, and I put a magic curtain here, and just said, this is connected to something behind the magic curtain, and I see no current flow, what do I assume is happening to these wires on the other side?
It's open or grounded.
An open circuit. Yeah. No currents flowing. It must be an open circuit. So for a capacitor, connecting it to DC looks like an open circuit. However, if I were to then take this and take the battery and flip it upside down, and here's my capacitor, I would then, I had pluses over here. What happens to the pluses? They travel back to the negative terminal, and the negatives travel back to the positive terminal. And then I end up with no charges over here. Eventually, this will repopulate with minus, 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 and plus, 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 plus. If I happen to flip it again, if I happen to flip that battery again, just before it becomes saturated with charges, and I do this with it, then the electrons move back to here, and the positive charges move back. And once again, I have this, and then this blanks out, and this blanks out, and I end up with pluses over here and minuses over here. That acts as though there's always room for current to flow, doesn't it? In other words, it's like there's nothing there blocking it. If I were to make the magic curtain again, here's my battery, except in this case, I'm not going to use a battery. It's a battery that continually flips back and forth in the form of a sine wave or something like that. This is known as AC, and this is DC. What do I think is behind the magic curtain if it doesn't present any resistance to me?
Just a closed circuit.
A short circuit, yeah. So a capacitor for AC looks like a short circuit. A capacitor for DC looks like an open circuit. Well, as it turns out, an inductor, because it stores energy in a magnetic field, doesn't like to have its magnetic field energy reversed. So what ends up happening with an inductor instead is that as current flows through it, you develop magnetic field lines which go around in coils that look like this. And because it does not like to have that direction changed, once it's, let's say I hook up a battery to it. Here's my plus and minus. It forms a magnetic field. What's an inductor made of? Physically, a coil of wire, right? It's a coil of wire. It's just a coil of wire. What does a coil of wire look like to DC?
Open circuit.
Straight wire.
No, it's just a straight, looks like a straight wire. Yeah. Doesn't care. It's just a wire. So coil just looks like a wire. What's the how much resistance to flow does a wire provide? A little bit, but not much. If I did if I did the curtain again, this at DC would give me a picture that looked like this. Here's the magic curtain. It looks like a short circuit for DC. If I were to do an AC circuit, can you guess what would happen?
Opposite.
It would be opposite. That's right. The same circuit for AC would look like an open circuit. So to review, we have a coil, which is an inductor, for AC and DC, and a capacitor. AC, this looks like an open circuit. This looks like a short. This looks like a short at AC and an open circuit at DC. Okay, so this is about how far we go when we do the technician class. Because, this is important stuff. I mean, this allows you to, for instance, build a filter circuit where you have, let's say, a power supply that looks like this. Anyone know what that's called?
Transformer.
Transformer. Okay. So we have AC. This is a magnetically coupled circuit. This uses mutual inductance, where you have two coils wrapped around an iron core, which allows you to have a magnetic circuit, which carries the magnetic field generated by the first side. This is known as the primary. And this is known as the secondary. You have AC voltage coming in and AC voltage coming out. And it is coupled together by coils that are turned around a common core, which is usually again made of iron or steel or something like that. So it generates a magnetic field inside. You generate and this only works with AC. And the ratio of turns that you have, N1 to N2, determines what the voltage ratio is. So if I have 100 turns over here and 10 turns on this side, I will have a ratio of 100 to 10, which is 10. That's my ratio, is equal to my voltage ratio. Let's say I have 120 volts AC over here over V2. If I do the math on this, I find that V2 is equal to 12 volts AC. So this is a way to use mutual inductance and coils to convert one AC voltage to another AC voltage. So what we also do with this is that we now can build a power supply from this, where we have this. We have 120 volts over here and 12 volts over here. And then we can run this through a diode. A diode, if we look at what AC looks like this. A diode is going to be a forward biased one-way street. So whenever the voltage goes above 0.7 volts for silicon or 0.3 volts for germanium, that's what diodes are typically made of. Internally, you have semiconductor material that has been doped with a little bit of impurities that make it more positive or more negative. If it gets over a particular threshold, it allows current to flow in the forward direction. What happens at that point is that if we look at that voltage waveform, well, this is the plus side and this is the minus side. The minus side basically gets canceled out, and we have a voltage waveform that looks like this. Because it only conducts during the positive side. So now what we have is we have this ugly looking DC because it never goes negative. This is actually really important. Because now we've converted AC to DC. This is known as a rectifier. Kind of like correcting something, I guess. It's rectifying it.
Half
This
wave.
is known as a half wave rectifier. because it's working on half of the current waveform or half the voltage waveform, the positive side only. And we then have to look at this and say, do you think our computer would like a voltage that looked like that?
No.
Depends.
Definitely not, unless it had some way of filtering it and making it clean DC. What we do there is we use a capacitor that charges up during the peaks and then discharges slowly during the dips. So now we have ripple, but it doesn't ever get to zero. Well, okay, if we've picked that, then we can then take that and we can run that through a Zener diode. A Zener diode is a backwards diode that has a voltage rating, and it basically, if the voltage gets anything above a certain voltage, it says, that's I'm not gonna allow anything higher than that to get through. So if I have a 5-volt rated Zener diode right there, what'll happen is that it allows higher voltage to basically dissipate as current going through it, and you end up with a flat voltage, which then ends up going out to your outside circuit. And now you have a nice, clean, this is a little bit simplified, voltage. And if it's 5 volts, what is that used for?
USB.
Anything computer.
That's USB charging. Yeah. So this is a very basic USB charger. Missing a couple of resistors here and there, but that's the basic idea. And there might actually be an inductor in there as well to block some of the AC, better filtering. So what we now have is using our capacitor and our inductor creatively, but we're kind of using them in the extreme. Well, another thing we can do, and I figure I should mention it at this point, is that we can make it so that here's our waveform again, our AC waveform. What if we, instead of just using the pluses, we actually want to use all the power generated by the pluses and minuses? Well, what we can do is we can say, okay, well, here's our AC power, and we can make two paths because half the time we're going to be looking like that. If we used a diode here and we take the power off of here and we run this through a capacitor and we run this through a Zener diode and we send this out to the world. Okay, so we come up through here and back down through here, and now we have to break this line. We give it a return path that looks like this, and it comes up to here, and then it goes up through some other point that goes up to here, and that goes down here over to here. Okay, that makes a complete circuit. But now we're going to say, okay, but how about for the other half when we have the plus down here and the minus here? Well, now we follow this path. And we come up to here, and we have to put another one, which is a forward one-way street. We come back down to here, and we have to go through here and like that. What we've now done is we've given the signal two different paths to follow, depending on whether it's plus or minus. And instead of a half-wave rectified signal, what we now have is, because it actually uses a different part of the circuit during the two halves, now we have a signal that looks like this. We've used more of the wave. It's a more efficient use of the power. This is called a full wave rectifier. And right here, we have a full wave bridge. That combination of 4 diodes is a full wave bridge. And we still use our capacitors and inductors to do all the filtering. Okay, so now that's power supplies. Well, what we're going to do now is show everybody that, well, okay, so a capacitor doesn't always act like a short circuit. Remember, for AC, a capacitor is a short circuit, and for DC, it's an open circuit. And an inductor does the other thing. This is an open, and this is a short. But that's in the extreme. AC, we're going to assume, means infinity frequency. The reason being, we now have to introduce another term. For a resistor, we have resistance, which is measured in ohms. We use the big letter R for that as well. Now, does a resistor care what the waveform looks like, whether it's AC or DC?
No.
It does not. So resistance is resistance. But now there's another thing, which is how something behaves when it's exposed to AC. Resistance is DC. Now we also have something called AC, and we have this other term called reactance. We use the big letter X. It's also measured in ohms. And for a resistor, these are the same thing. It doesn't make any difference because a resistor does not care. However, capacitors and inductors, it does matter. For a capacitor, its resistance, remember that DC is infinity. For an inductor, its resistance is zero. But then there's this other term, which is frequency dependent, which is the big letter X. For a capacitor, it's -1 over 2 pi FC. And actually, it really isn't negative there. It'll include the negative there in a minute. So, and I did that wrong. I wasn't thinking. 2 pi FL. Okay. Pi, that's the same old pi that you recognize as 3.14159. If it's Pi Day, March 14th is Pi Day because it's 3.14, 314. 2 is just 2. What is the letter F that shows up in both of these?
Frequency.
Frequency.
Frequency, okay. And C is capacitance, which is defined by the physical characteristics of the device. And L is inductance, which is defined by the characteristics of the device, the number of turns, the length, the thickness of the wire, etc. Capacitor is defined by the size of the plates, the spacing of the plates, basically how much charge it can hold. But what's really important here is that once you've established those two mechanical devices, if you change the frequency, what happens to these values of X?
They're inversely proportional.
They are. And not only that, you have frequency dependence. Depending on what the F does, that determines what the X does, because there's an F term, which is frequency, in both of them. This is really important, actually, because that means that if we, let's make sure we did this right. So we're going to erase that and say, okay, what is the frequency of DC, everyone?
0.
0. Okay. So what happens if we put 0 in for F? We get 1 over 0. What's 1 over 0?
Undefined, infinity.
Infinity. Well, guess what? We already said that because the resistance is 0. We obviously did that right. How about for the inductor? If we use a 0 here for F?
0.
We get 0. And we already calculated that one as 0. So we did those right. Okay. The next part is that we now have these frequency dependent things. And that makes things both very interesting and a little more complicated because they're frequency dependent. So for an inductor, this is actually an easy relationship because as frequency goes up, it just goes up. But for a capacitor, as frequency goes up, it goes down. And it looks like that. Okay, so what this means is that when frequency changes, our values change. Our values of reactance change. X is reactance. Okay, now the other thing is that reactance adds just like resistors. A resistor in series with another resistor will divide the voltage based on what those resistor values are. The sum of these two resistors put together, hold on a sec. I lost my screen. Ooh. Come on.
Loose connection.
Come on. Yeah, loose connection. Okay.
Ghost in the wires.
Must have been a software update. Okay. So we now have for XL 2 pi FL, where XC is equal to 1 over 2 pi FC. Well, we can do certain things with these. We can actually take these. We're looking at resistors. I remember we were doing that. The sum of these two resistors in series is R1 plus R2. They just simply add because current has to flow through both of them in series. For a resistor in a network that is parallel, the current splits, which means that the overall path that it has to take is actually easier than it would be if it were either just one or the other. So for this network, it's R1, R2 over R1 plus R2, which is actually smaller. This is times. It's actually smaller than either of them. Well, reactances don't behave exactly the same way because reactance is actually just a component of something else called big letter Z, which has this name, which we talked about yesterday, which is impedance, which is how something behaves when exposed to alternating current. At this point, what we have to do is say that we have to state another formula. Z is equal to R plus IX for an inductor. And R minus IX for a capacitor. So what is important about that? What do you see about that that's important?
They're opposite of each other.
They're opposite, yeah. Okay, so the other thing is that that letter I there represents what's known as the imaginary term. And it's not really imaginary, it's very real. But what it means is that when we are plotting this on a graph, it means that reactance is perpendicular to resistance. What I mean by that is if this is resistance, that's the x-axis, reactance is on this axis. They are perpendicular to each other. This is actually an extremely important distinction because let's say that we have a device that is 3 ohms resistive and plus 4i ohms in the reactance direction. We can write that as 3 plus 4i ohms. What is the length of that line by Pythagoras' theorem? That is 5 units. So if we could say that Z is equal to 3 plus 4i ohms, we could say that the magnitude of Z is 5 ohms. So 3 plus 4 equals 5, right?
Yes.
Right, everyone?
Yeah.
So in this case, 3 plus 4 actually kind of does equal 5, except that there's now an angle between them, which relates the sine and cosine of those things. So we could break this down and say that it is actually 5 ohms with an angle theta of about, oh, what is it? 57 degrees ohms. All right. So what does this mean? It looks kind of confusing, doesn't it? Well, what this really means is that we're going to write Ohm's law. Everyone remembers Ohm's law?
Yep.
Okay. Except that we're not really using R anymore. We're using Z. Which means that if our Z looks like this, now we're going to go back to drawing that circle that we had. And we have an angle of 57 degrees and a magnitude of 5. And our impedance is 5 angle 57 degrees ohms. It actually shows up here. And we have current that starts down here. Where will our voltage show up? Here we go. We have to replace this. E is equal to IZ. So our E is equal to whatever the I was times 5 angle 57 degrees, which is equal to 5 times I, angle of 57 degrees. So if we have current that looks like this, our voltage will actually be like this, 5 times bigger, because that's what the math said. But it will be, what do you notice about it?
It's phase shift.
It's shifted. It's shifted
Lagging.
by 57 degrees. The voltage is actually leading the current if you were to measure the two. And that is because of the reactance of that thing. You would actually see a phase shift, which can max out at 360 degrees or have negative 360 degrees. You would have a phase shift between voltage and current of 57 degrees. So not only would the magnitude come into play, but it would actually shift the phases. The other thing that happens is that now, what if we have a black box and we call this Z1, and we have another black box and call it Z2? Impedances add just like resistors. What if this is actually a capacitor and it has an impedance of minus I over 2 pi FC, and this is an inductor, and this has an impedance of 2 pi FL. What are the what are the signs of those two? The first one, is it positive or negative?
Negative.
It would be down here. What would the second one be? Positive or negative?
Positive.
Positive.
Up there.
Could I make them equal and opposite? What would happen if they were equal and opposite? What would the end result be?
You'd be at resonance.
You'd be at 0. This is called resonance, which means that these things cancel each other out and just look like a short circuit. This is actually really important because I can actually calculate this value. I can calculate where it happens because I know that minus 1 over 2 pi FC plus 2 pi FL is equal to 0. And I can calculate F is equal to 1 over 2 pi square root of LC. That is the resonant frequency. This is known as a tank circuit or a resonant circuit. And what happens to my impedance when I'm at that one particular frequency?
It would equal 0.
It goes to 0. Yeah. My impedance curve looks like this. And that goes all the way down to 0. This is really important because now I have the basis for something that has no impedance at how many frequencies?
1.
One, exactly one frequency. That is my resonant frequency. This is now a tuned circuit. By changing the value of the L and the C, I can make this circuit behave in different ways. I can make those two devices resonate. This is the basis of what we call an oscillator or a filter, depending on how we build it. An oscillator generates one frequency better than all other frequencies. If we want to make an oscillator that makes a frequency of 3.1062598 using a capacitor and an inductor, we can do that. Other frequencies will not be able to propagate. This one, based on how we pick those two frequencies, will. If we have a filter, we can build a filter based on capacitors and inductors that passes 3.1062598 megahertz better than all others just by choosing our values. So this is actually a really, really profound thing because if we are now creative about these things, we can build a filter that, if our frequencies go from 0 to infinity, looks like this, where it blocks everything except for this very tiny range. We can also build a filter that looks like this. We can also build one that looks like that. We can have the intersection of two of them, which allows a certain band to get through and not others, for instance. Depending on how we design it, we can do all kinds of cool stuff with, and what did we start again with? Just two devices. Capacitors and inductors. Yep. Okay. So now, now that we've covered that, and I know that's quite a bit to take in, but now we're going to go back to the book and see what the book says. Okay, what is reactance? Opposition to the flow of alternating current caused by capacitance or inductance. Okay. What letter is used to represent reactance? Big letter X. We measure reactance in ohms. And how does an inductor react to AC? It's a linear function, and it's because the reactance is equal to 2 pi FL. It's a linear function. There it is. X is equal to 2 pi FL. For a capacitor, the reactance is 1 over 2 pi FC, which is why I like this book. You know, it doesn't give too much information, but it gives a good starting point. So for a capacitor, as the frequency increases, the reactance decreases. Impedance is a ratio of voltage to current. Because of Ohm's law, it works into Ohm's law. E equals I times Z, big letter Z. Ooh, the inverse of impedance, this is just something you have to memorize. That's called admittance. You can have an impedance matrix. We actually also did an admittance matrix when I was in college. Instead of the letter Z, it uses the big letter Y. So here you go. Honestly, in all my years of engineering and amateur radio, I never had an occasion to use admittance, but I did have to learn it in college. So that's true. What happens in an LC circuit? LC, capacitor, inductor, inductor, capacitor. At resonance, inductive and reactive capacitances cancel. What happens when inductive and capacitance reactance are equal? Resonance causes the impedance to be very low. They cancel. It makes a nice, easy path. And finally, which of the following devices can be used for impedance matching at radio frequencies? Okay. We didn't cover that one yet, and we're going to cover it right now. Okay, so again, what is impedance? R plus IX. We look at it like this. Well, as it turns out, if we have our R-axis and our X-axis, if we are over here a little bit, what would we add to this circuit to cancel? Well, let's ask this first question. Is this as shown, is this an inductive or a capacitive reactance? Being that this is positive and this is negative.
Inductive.
That would be inductive because it's positive. So we started with an inductive reactance. How would we cancel the reactive part? What would we add to it?
Capacitor.
We'd add a capacitor. Yep, we'd add a capacitor. If it was the other way, and we started here, down here, that would be a capacitive reactance. And what would we add to cancel it?
An inductor.
You'd add an inductor. Yep. And how would we size it?
Equally.
It would be the equal size. Well, it would be the equal reactance. And from that, in order to pick the value, we have to remember that XL is equal to 2 pi FL. So that means for one particular frequency F, we could pick a value L for which that was true. That's why it's a tuned circuit. Okay. Another thing we can do to with these devices is we can also, and this is actually on the extra class exam, to do impedance matching. So let's say you have a Z out here of some value. By adding a length of transmission line, which is like coaxial cable, at a given length, at a given frequency, which determines how long it is, this can actually act as a transformer. There's something called a Smith chart that you will get to when you get to your extra class exam. And the way that a Smith chart works is that well, I can show you all during the break if you really want. But Z in times Z out is equal to characteristic impedance squared. So this is Z out and this is Z in. And for a quarter wave transmission line, this holds true. So you can use a transmission line to transform an impedance. The most familiar one is a coaxial cable. Another one you can do is, we covered this very briefly, but what is this thing called again?
Transformer.
A transformer.
Step down. Step down.
That in particular is step down. Okay. So we're going to make a turns ratio of N1 and N2. We're going to make this ratio N1 to N2 is 2 to 1. So we have our voltage and voltage 2. So we don't know how many turns it is. It doesn't matter. Only the ratio matters. We just know that there are twice as many turns on that side as we have on the secondary side. Again, this is called the primary side, and this is called the secondary side. The way that this works is we're going to say that we have 100 volts over here. So N1 over N2 is 2, because it's a 2 to 1 ratio. That's a turns ratio, is equal to 100 volts over V2. So from this, we know that V2 is equal to 50 volts. It's AC or DC, everyone?
AC.
AC. Okay. Right. So we have 50 volts AC. Okay. So now we can say how much power is going in on this side and how much power is going out over there. Well, all we know is that power is conserved. We don't know exactly how much power is going out. So we can say, what's our formula for power?
PIE.
Yep, P is equal to I times E. Okay. Is equal to I times E. Agreed? On both sides. Okay. So we have I1 times E1 is equal to I2 times E2. Okay. Well, we know that we have E2 and we have E1. So we can say that the ratio of I1 divided by I2 is equal to E2 over E1 is equal to 50 over 100, which is a half. So there's half as much current going in as there is going out, whatever that value happens to be. So we can now say I1 or I2, we'll go I2 is equal to 2 times I1. And what do we also have? V1 is equal to 2 V2. Okay, so I'm going to erase some of this so we have a little more space. And now comes the truly mind-blowing part. On the left-hand side, you ready? What is resistance or impedance? What's the formula? We go back to Ohm's law.
E equals I times R.
Right. E equals I times R or equals I times Z, depending on which one you want to use. Okay. For this case, we're going to use the letter Z. So we're going to rearrange this. Going to go back to making the circle. Like that. Always go back to making the circle. Well, we know I and E, Z is equal to E divided by I. So we now have these ratios over here, and we can plug these values in. We can actually plug information in and make these make some sense. So Z equals E over I. So we're going to say that Z2 is equal to E2 divided by I2. And we're going to say that Z1 is equal to E1 divided by I1 because we're allowed to do this. It's math. We can do anything we want. Well, now we can take this Z2 and we can take the values for Z1 and E1. Can look up here, 2E2. And the other one, I1, is equal to 1/2 I2. Well, see this E2 over I2 right there? Well, we already said that's Z2. And what's 2 divided by 1/2 is 4. So now we get Z2 is equal to, Z1 is equal to 4Z2. Does anyone remember what our turns ratio was?
2 to 1.
2 to 1. What's our impedance ratio?
2 to 1.
No, it's 4 to 1.
Oh, that's right.
2 squared.
So the turns ratio is now squared to get it. So if we had a turns ratio of 10 to 1, what would our impedance match be?
20 to 1?
No, it'd be 100 to 1 because
Oh,
it's the
okay.
square. If we had 6 to 1, it would be 36 to 1, which is actually really important because if we have, let's say, a 10 to 1 ratio and we have a resistor over here that is 5 ohms, what would our resistor look like on the other side? We would look at it would look like 500 ohms. We don't need to know what's over there. As we're looking into this thing, it would make that 5 ohm resistor look like 500 because it's changing the currents and it's changing the voltage. It makes it appear as something that it's not. So if we have an antenna over here that has an impedance of, let's say, 3 ohms, what would it look like on the other side?
30.
No. The ratio is 10 to 1.
300.
It would look like 300 because it goes up as the square. Yep. And what's cool about this is that not only does that work like that, but what if the impedance is 3 ohms plus I 3 ohms? It would actually convert it to, it doesn't care what the form is, 3 ohms, 300 plus I 300 ohms. It just multiplies it by the square of that ratio. And that's how you use a transformer for impedance matching. We actually do that all the time. It's used for matching microphones, high Z to low Z. Has anyone ever seen a microphone that says it's a low Z microphone? Or a high Z microphone? If you use it for let's say music, Has anyone ever seen that?
Yep.
There you go. That's a high Z microphone or a low Z microphone. Z is impedance, and that's how you can use a high Z on a low Z circuit or a low Z on a high Z circuit. Okay, so we're moving into decibels and voltage dividers and current dividers. How about a 5-minute break, everybody?
Works for me.
Okay.
Please.
Is this where you're going to explain the Smith?
Yeah, I can explain the Smith chart.
Okay, thanks.
Okay. Okay. So this beautiful thing is called a Smith chart. And let me make it.
It's not on the screen yet, Scott.
Nope, it's not on the screen. Here we go. Okay. Okay, this is called a Smith chart. Yeah. That's not a very good version of the Smith chart. Let's find a better one. Let's find a better one. Okay. And let me go back to this. For those of you who want to know. Okay. This is a Smith chart. So the way that a Smith chart works is that you have in the center. Oh, stop. There we go. So you have two axes. They are a resistance axis and a reactance axis. Essentially, you have the one of the axes, which is then curved into circles. The other one is curved into curves. So basically, it's what somebody figured out was a good idea to do is take space, which looked like a grid, and bend it into circles and curves. And what ends up happening is that this is a way to match one impedance to another one graphically. And by the way, it's going to get less technical as we go. I just need to cover the technical stuff first. And what ends up happening, notice that these rings around the side or around the outside start at, for instance, 0 right there. And as we roll around, there's arrows and it says 0.1, 0.12, 0.13, etc., 0.25, and then it comes all the way around back to 0.49. So this is a way of figuring out, it'll say wavelengths toward source or wavelengths toward load by looking at the impedance of a transformer or by looking at the characteristic impedance of a transmission line, you can start at one point, work by using essentially a compass and making circles, figure out what the starting impedance is going to be and the ending impedance is going to be by looking at how long the transmission line that you added is. And since it basically all the way around one full circle is a half wavelength, well, what it really means is that a half wavelength transmission line will start at one point and go, and I don't know if can you see my cursor or not?
Yes, I can.
Okay. So it'll start at one point, for instance, and this is an eighth of a wave. Going all the way around to here is a quarter wave. And you get back around to multiples of a half wave, and you're right back where you started. So by looking at this, if we say that our normalized impedance is 50 ohms and we're at 0.4, that means that we start at 20 ohms because it's 0.4 times 50. If we come all the way around to the other side, back over here, we'll see that we're at about 2.5. So we have transformed a 20 ohm impedance to 2.5 times 50, which is 125 ohms. This works not only for resistances, it works for impedances. So it actually, by looking at where you are on the curve, you may be starting up here where my cursor is and not flat on this axis, in which case you have resistance and reactance. You go halfway around and it takes you to a completely different point where it was the resistance has changed, but also now the reactance has changed also. And you've gone from capacitive to inductive or inductive to capacitive just by putting in a piece of transmission line as a transformer. And
Thank you.
It's kind of magic, but what it really does is this chart, which was put together, about 75 years ago, it makes it possible for somebody to avoid doing all the mathematics because the mathematics is actually quite complicated, or it can be very complicated. It allows them to basically do it with a ruler and a compass and just make circles and say, here's my starting point and here's my end point. Oh, 1939. So it's been 85 years by Philip Smith.
I recently purchased a nano VNA, which has this capability on it.
Yep.
And to show me, exactly when that transmission line or the antenna is an impedance matched or in the center, the dot.
Yep. The center is your normalized impedance. So you start at 50 ohms, but because it's normalized, it could be, let's say you have a 600 ohm normalized impedance. You have a 600 ohm match to match. You set that center point. You say, okay, I'm going to start at 600 ohms. That's my basis. I'm going to go to the center. And then depending on what I'm using, I'm going to multiply it by some factor. And so long as you renormalize everything, it gives you the correct value.
Okay, I've got a side question to ask you.
Mm-hmm.
It's on it, and I never realized it until I got the Nano VNA, but I saw it in the extra class. I think talking about in the test. Could you give me a brief synopsis? What is S11, S21?
Okay, that comes from a multi-port system. Those are port names for network analysis.
And I think that
S11
the 11 is
into and measured into, and then the 22 is out and out. But you can also have cross values, which are 21 and 12, because each one is like a two-port system. It's essentially looking at network analysis, which is beyond this class. but there's a whole there's a whole bunch of articles on this kind of thing. I'm sure YouTube actually and Wikipedia.
I've gone on YouTube and watched every video I can, on it.
Yeah. And it's basically network analysis. It's looking at, okay, here we go. Looking at reflection coefficients. Those are S11 and S22. And S parameters are used to characterize transistors and calculate many properties, including input and output impedances, maximum gain, instabilities, transducer gain. So yeah, it's basically just looking at it as network analysis. They're network analysis ports.
Okay.
And
Thank you.
How one port relates to another one. From something to something. From 1 to 2, what is the difference? What's what's a multiplication factor? What's a phase shift? Things like that.
Question, Scott.
Yeah.
Going back to the Smith chart, what does that uppercase gamma stand for?
Ooh, That is a very good question. I have to look at it again. Smith chart. I will have to look because I don't remember.
Okay, thank you.
All right, ready to move on? It gets easier. We've got some foundational stuff that we've just done, which is really important to understand where it comes from. And now we start to get into how to use it. Okay, decibels, current and voltage dividers, electrical power calculations, sine root means, sine wave, root mean square values, and peak envelope power. All
I
right,
just thought it
so
was
now,
easy.
yeah. So, okay. So, does everyone agree that looking at this schematic right here, that the current flowing out of the battery has to be equal to the currents flowing through both resistors, the sum of those currents?
Yes.
Yes.
Yes. Okay. At point A, there is Kirchhoff's current law. Kirchhoff was another one of those 1800s scientists who said, oh, well, the current flowing in, because an electron, we don't know what they are yet, but electrons are things. A number of electrons flowing in has to be equal to the number of electrons flowing out. You can't have an accumulation if you don't have a capacitor in there. So point A is called a node. A node is basically just a point in space. You cannot, where you cannot have an accumulation. So at any point that is a node, your current flowing in has to be equal to your current flowing out. Now, it's also true by Ohm's law. Ohm's law is E equals I times R. So if I were to measure the voltage across resistor 1, I have a resistance and I have a current, which means I must have a voltage, right?
Yep.
Same thing across R2. Well, that also means that those voltages must be the same because the voltage provided by the battery, given the way the wire is built on top and bottom, must supply the same voltage to both of them. Well, if I1 R1 equals I2 R2 and R1 and R2 are the same, then your currents will be the same. If your resistors are of different values, then your currents will be different. This is a current dividing circuit where the current is divided based on the size, based on the values of the resistors, the resistance values. So that is a current divider circuit. These are in parallel. Okay, so now if I were to do a voltage dividing circuit, and let's say I have a battery that is 10 volts, and I have a 1 ohm resistor and a 9 ohm resistor, and I have a current flowing out, is the current going to go through both of the resistors?
Yes.
It has to. That's right. Okay. What is the total resistance encountered by that current? How many ohms?
10.
Okay. 10 ohms. Okay. So by Ohm's law, E is equal to I times R is equal to, we have 10 is equal to 10 times I. Current is equal to 1 amp. Okay. So we have 1 amp. Now we're going to do individual voltages. We develop a voltage across the first resistor. We're going to use Ohm's law again. E is equal to I times R is equal to 1 amp times 1 is 1 volt. If we were to measure right here using a voltmeter, we would see 1 volt. Well, you can probably guess what's going to be across the other one. E is equal to I times R is equal to 1 amp times 9 ohms is 9 volts. A voltmeter, and we would measure 9 volts. Okay, so two resistors in series can function as a voltage divider because they experience the same current. So that would be a voltage divider network. So a very simple use of something like this would be, if you don't mind burning up a little bit of heat, let's say you have a circuit that only requires 1 volt and all you have is a 10-volt battery. You could pick this off and pick this off and deliver it to that circuit that you need. And how much voltage would it receive?
1 volt.
1 volt.
1 volt. Yeah. You just made a different DC voltage for use somewhere else. Okay, so now we're going to do another mathy thing. Okay, here we go. We're going to look at sine waves. Oh boy. This is actually really important. We're going to look at sine waves and RMS and peak envelope power and decibels and stuff like that. Here we go. Okay, so I can't draw the graph as well as they do. So this right here is what we would typically see if we looked at our wall socket. How many volts would we measure if we used a meter? How many volts?
120.
120 volts. Okay. At what frequency?
60 hertz.
60 hertz, unless you're in Europe, in which case it's 230 volts and 50 hertz. Okay, so what we're going to do now is take a look at this curve, and we are going to duplicate this curve as best I can. Okay, this is called 120 volts AC, as we see in our wall circuit at 60 hertz. Okay, now what I am going to ask is, what voltage would we actually see if we plotted this out on an oscilloscope? What would that peak voltage be? It would actually be about 170 volts. And we would also see negative 170 volts right here. Even though this is colloquially called
peak to peak.
Volts. Peak to peak, yeah. This is 120 volts AC. This is 120 volts AC. This is known as RMS. Okay.
0.707.
Okay, but here's why. Okay, so if I have a 120 volt DC power supply, and it is run through 1 ohm, we're going to do Ohm's law for power. $120. Does everybody agree with that? Using Ohm's law for power?
Yes.
Okay. We get 120 watts. Now, if we were to instead look at, we're going to make a little note up here that says we got 120 watts. We're going to look at this circuit, and I'm going to ask, using Ohm's law for power, P is equal to I times E. How much power are we making when we are at 0 volts?
0.
Because 0 volts. Yeah. How about when we're at 0 volts?
0.
Yep. How about over here at 0?
Another 0.
Another 0. But how about up here at the very top?
170.
Yeah, it's 170 is P is equal to I times E. And oops, I think I did that wrong. Hold on. We're going to do that right. P is equal to V squared over R. I did that wrong. Okay. So it's 120 volts squared divided by 1 is 14,400. Okay. There we go. 14,400 watts. Okay. So now we're going to look at the same thing, but we're going to use 170. B squared over R. So it's 170 squared divided by 1, which is 28,900 watts. Well, okay, what's the problem here? Is that the same?
Yes,
is that the same?
Yes.
No, it's not. Not at the peak, it's not. We're making a
Well,
lot.
if you multiply it times 0.707, it is.
I don't think so.
No, let me try.
No,
900.
definitely not. So what is happening here is that at the peak, we are making a lot more power than 14,400. In fact, it's over
Oh, yes.
twice.
Yeah.
It's over
Right.
twice.
Right.
So what happens at this point where it's 120 volts? We're making exactly 14,400 up here. And how about down below where it says negative 170? What's a big negative number squared?
Positive
number.
Positive. Yeah. Okay. So it doesn't matter if it's positive or negative. We just care how far away from zero it is. So, but how about all these areas like down in here where we're nowhere near the peak? How much power are we making there? It's somewhat diminished, right?
Yeah.
Okay. So if we were to take, because we know that power is equal to V squared over R, because power is equal to E times I, and E equals I times R. We can substitute that in, and we can get power is equal to V squared over R. That's where that comes from. If we were to take that and we were to look at the time average over an entire cycle, we would basically be doing something called an integration over one cycle of V squared over R for all time. Well, we're not going to go into the calculus of that. What it turns out is that we have what it turns out is that we have chosen to pick a voltage that makes the same amount of power as an equivalent DC. And we are calling that an RMS, which is a root mean square power, root mean square voltage. So 120 volts RMS is this sine wave that peaks at plus 170 and goes all the way down to minus 170. So if you look at it on an oscilloscope, you will see peak to peak of 340 volts. And you will see peaks of 170 and negative 170 volts. So in your wall, which you call 120 volts, you actually have voltage that oscillates between plus 170 and negative 170 because it makes the same equivalent amount of power that 120 volts DC would make. And this is known as RMS or root mean square. Now, as it turns out, that relationship between 170 volts and 120 volts is square root of 2, which is 1.414. So how you find your peak voltage, you take your RMS voltage for a sine wave only. It only works for a sine wave, and multiply by 1.414. So if I had a 10 volts RMS, what would my peak be? 10 times 1.414 is 14.14 and negative 14.14 when I drew out the sine wave. This is known as RMS. Now, as it turns out, this is actually a very important distinction because when you go by a voltmeter, it might say reads AC. It could also say AC true reading. Because which wave is going to make more power? One that looks like this or one that looks like this? The top one or the bottom one? Yeah, the one on the bottom is actually going to make a lot more power. So when something is a true reading AC voltmeter, it's going to actually tell you what that power capability is. If it's just an AC reading meter, like a cheap voltmeter, it's going to assume that you're looking at a sine wave.
Your Harbor Freight.
Yeah, exactly. That's your Harbor Freight meter, which is not a true RMS reading meter. It does make a difference. Okay, so now we go back to this. What value of an AC signal produces the same power dissipation as a resistor in a DC circuit? RMS.
The RMS value.
RMS. What is the RMS voltage of a sine wave with 17 volts peak? Well, there's that peak. We would take the peak and divide it by 1.414,
1.414.
and we get 12 volts. The peak value, the peak to peak voltage, that means from the top to the bottom of 120 volts, it goes up to 170 and down to negative 170, which means we get about 340 from the top to the bottom. Okay, now power. How many watts of electrical power are consumed if 400 volts is supplied to an 800 ohm load? What's the equation we use for that? P is IE. We can reform this as P is equal to V squared over R. Using substitution, we have a voltage, we have a resistance, we get 400 squared divided by 800, we get 200 watts. P is equal to V times I, or IE in this case. Here's another form. How many watts are consumed when 7 milliamps flows through a 1250 ohm resistance? You could go through and calculate the voltage, or you could just change the Ohm's law equations around. This is the other one. P is equal to I squared R. So there's 3 different versions. P is equal to I times E. P is equal to E squared over R. P is equal to I squared R. Those all come up with the same answer. And they're all related because E is equal to I times R. You can always just substitute that in and rewrite your equations. If you use them enough, they kind of become second nature. RMS voltage of a 50 ohm dummy load dissipating 1200 watts. Okay. Well, here's V squared RMS is equal to P times R. This is this is a modification of P is equal to V squared over R. They're asking for RMS. You end up with the square root. It ends up 245 volts. Does anybody want to see me calculate that one out?
I would actually.
Okay.
I'm sorry.
I was gonna say, I would too.
Okay.
Get out.
Okay. Okay, here we go. So let me go back and just take a look at that one and make sure I'm grabbing the right thing. Okay. Here we go. 50 ohm load and 1200 watts. Okay. So we can do this directly, right? They're asking for RMS voltage. What does RMS voltage mean? It means the equivalent DC voltage, right? That's what RMS means, which means we don't have to calculate peak to peak or anything like that. Okay. Well, we have P is equal to I times D. And E is equal to I times R. So we can rewrite this. We can write this I squared times, we take the E and plug it in, I squared R. We could also rewrite this by plugging in the I is equal to V squared over R. And this is the one that would make the most sense because they told us the power and they told us the resistance. Okay. So now we can multiply both sides by R. So P times R is equal to V squared. And this is going to be RMS already because they wanted to know what the voltage was. This is an average voltage. Well, power times resistance. They told us that it's 1200 watts times 50 is 60,000 is equal to V RMS squared. To do that, we just take the square root. The square root of 60,000 is equal to, by calculator, you will need a calculator for this exam, probably, 245 volts. Now, if they were to say, what is the peak voltage in that voltage, it would be 245 volts RMS. What would be the peak voltage we would see?
Times 1.414, right?
Yep, times 1.414. Anyone have a calculator handy?
Yeah.
What is it?
45 times 1.414 is equal to 346.
Okay. And we would also have a negative peak of 346 volts. So if they said what was the peak to peak voltage, we'd see 692 volts. That would be the volts peak to peak. And that's actually known as P dash P, peak to peak.
Calculator has to be non-scientific.
Yeah, it has. No, it can be scientific, but it has to be can't have anything in memory.
Okay.
So
no
your peak.
graphing calculator.
No graphing calculators.
The one that they've most recommended is the TI 30XS, and that's what I've got.
Yep.
Because you can plug in the formula straight across.
Right.
And it'll give you the answer. So TI 30XS.
So
and they're about $20.
Yeah. Okay. So here's another one. We're looking at peak envelope power. Okay, so the PEP is peak envelope power. The ratio, and this is just memorization. PEP to average power is a ratio for an unmodulated carrier is 1.0. For an unmodulated carrier, if the average power is 1,060 watts, it's 1,060 watts. Okay, let's see. PEP produced by 200 volts peak to peak across a 50 ohm dummy load. Okay, so for this one, we're going to actually do the calculations. Okay, here we go. Okay. Da, da, da. Okay, 200 volts peak to peak. Okay. What does it mean, peak to peak? This is where we actually have to draw it. What does that mean, 200 volts peak to peak?
From the top of the negative, top of the positive to the bottom of the negative.
Yep, that means you have plus 100 and negative 100. So what is your peak voltage?
100 volts.
100 volts. So what is your RMS?
About 70?
Yep. Because 100 is RMS times 1.414. So to get it, you would divide it by 1.414 and you get about 70 volts. Okay. So now P is equal to I times E. E is equal to I times R. And we have a voltage. They told us what the resistance was, right? They said it was a 50 ohm resistance. And we have a voltage. So what we need to do is substitute the I that goes in, and we get P is equal to V squared over R. Is 70 squared divided by 50, which is about 5,000 divided by 50, which is 100 watts. There we go. That's the answer. That was the answer in the book. Y'all want to do the next one too? What is the output of a 500 volt peak to peak across a 50 ohm load? Okay. What does 500 volts peak to peak mean?
250
250 plus and
Top on
250
that.
minus.
Right. 250 and negative 250. Okay. So what is the RMS value? How do you get it?
About
Divide by
177.
1.14.
Divide by 1.414. And what do you get?
177.
Okay. I'll take your word for it. Okay. So power is just, we're just going to write V squared over R is equal to 177 squared divided by 50. What do we get?
626, about 627.
626. Okay. The answer in the book is 625. That's probably right. Okay. Notice. Okay. Who was here for the technician class we just did?
I was.
Okay. So remember I wrote down that painful formula, which was logarithmic stuff for calculating decibels.
Yeah.
Yeah. Well, look at this. Does that look familiar?
You're not sharing your screen.
Nope, I'm not. But the very next line, and I'm going to share the screen right now.
The bottom of page 11.
Yep, bottom of page 11. 10 log 10 of P2 over P1. Do you remember that from class?
Yes. Yes.
There we go. That's how you calculate decibels. So now that we have the magic formula that we talked about, we have decibels is equal to 10 log base 10 of P2 over P1. Okay, so we're going to double. We're going to go up by a factor of 2. So whoever's got a calculator, 10 log base 10 of 2. You just got a log button, and this is approximately equal to 10 times 0.3, which is 3 dB. And that's how we get it. Because the log base 10 of 2 is roughly 0.3, because 10 to the 0.3 power is approximately equal to 2. We can do this. We can use this for all kinds of other stuff too. And it doesn't have to be exact values. So let's look at the next question. Okay. What dB change represents a factor of 2? Approximately 3 decibels.
Mm-hmm.
Okay. When P2 over P1 is less than 1, it means there's a power loss. That makes sense because it'll end up with a negative value for the decibels. So what percentage of power loss is equivalent to a loss of 1 dB? Well, we would have to, if we really wanted to do the math, we could figure out that the 1 decibel turns into negative 0.1, and we could do that. 10 to the minus 0.1 is 79%. What's important to note is you can calculate that if you really need to. It turns out that 1 dB is about 20% power loss. Okay, resistors. All right. This works for impedances as well. Resistors in series do what?
Add.
They add. Okay.
So.
Resistors in parallel do not
average.
Add. What you end up with is, you have to remember this formula. R total is equal to R1, R2 over R1 plus R2. So if in the book we had, let's see, what were the values? What are the values in that book? 100.
100 and 200.
Right, 100 ohms and 200 ohms. Well, we can do this and figure out that it's 100 times 200 divided by 100
300.
plus 200 is 20,000 divided by 300, which is about 67 ohms. If we have three of them, we could actually go through and calculate that as well. So here's one, and here's two, and here's three. We have a 10, a 20, and a 50. It's R1, R2, R3 divided by R1 plus R2 plus R3. Oof, that looked ugly. Is equal to 80 divided by, oops, 80 goes on the bottom. Let's see, 1 times 2, let's see, it's 1,000, 10,000 divided by 80. No, I did that wrong. Yeah, let's do that again. Yeah, you can't simplify it when you do that. It's 1 over R1 plus 1 over R2 plus 1 over R3. There we go. That looks better. So you have to calculate it like that. You can't simplify it. It works. You can simplify it if it turns out there are three of them that are exactly the same. But the end result is that if you have all these in parallel, they will end up being smaller than any of them connected. Yeah, the reciprocal of the sum of the reciprocals. Thank you, Brian. Okay, next. Inductors. I have two inductors in series.
Same. Add.
ZL1, ZL2, these add together. If I have them in parallel, it's ZL1, ZL2 over ZL1 plus ZL2. And the same thing if I have three of them, again, as I just showed, I can't do it that way. It's 1 over ZL1 plus 1 over ZL2 plus 1 over ZL3. So inductors behave the same way as resistors do. Capacitors, on the other hand, do not. If I have a capacitance here, let's turn it sideways. Versus this one is a little confusing, but this one down here, this is actually really easy to think about because these are now in parallel, and because each plate physically gets bigger, these guys add, right? This plate and this plate make a bigger plate. This plate and this plate make a bigger plate, so the capacitors get bigger. These up top, you use the 1 over ZC1 plus 1 over ZC2 plus 1 over ZC3. And for these, they just add. So capacitors are calculated the opposite from inductors and resistors. Okay, so the next question is if you have a 20 millihenry inductor in series with a 50 millihenry inductor, okay, they're in series. If they're in series, you draw them like this, 20 and 50. Those add together, that gives you 70. If you have three of them in parallel, notice they didn't make you actually do a complex calculation. If this is 10 and this is 10 and this is 10, it turns out that it divides by 3.
Right.
The end result is 3.3. Again, capacitors behave the opposite way. A 20 microfarad capacitor in parallel What will happen to those?
70.
That will give you 70 microfarads. If you put them in series, you will have to do the other thing. 20 and 50. And because you only have two of them, you can do 20 times 50 over 20 plus 50 is 1,000 over 70 is equal to about 13. Okay, the book says 14. Okay. And just to make things more complicated, of course, and we're on page 15 now, what is the equivalent capacitance of two 5 nanofarad capacitors and 1 picofarad capacitor in parallel? What are they trying to do to make this confusing to you?
Nano and pico.
Yeah, they're trying to combine. Is it page 21 it's the page that's labeled 15. It might be the 21st. Oh, it's in the book, book. Okay. Okay, and 1/750 picofarad. Okay, so here you have to convert nano to pico, and you have to know what the difference is. Nano
Minus
is
9.
10 to the minus ninth, and pico is 10 to the minus 12.
12.
Which means that there are 1,000 picos in 1 nano. A pico is 1,000 times smaller, so there are 1,000 picos in 1 nano. And so if you were then to convert these nanofarads to picos, it would be 5,000 picos, and this would be 5,000 picos. And these just add. So you would then, because they're in parallel, get 10,750 picofarads. If you converted that to nano, you would divide it by 1,000, you'd get 10.750 nanofarads, which is the answer in the book. What causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected? That would be mutual inductance. You basically are creating a magnetic field in the core, and it's being transferred to the other device. Transformers. Okay, let's switch back over to the book. Oop. Here we go. Transformers. If you have a 500 turn primary and a 1,500 turn secondary, what is the turns ratio? Primary divided by secondary would be 500 divided by 1,500, which would be a third. That is proportional to the voltage ratio. So if you have 120 volts on the primary, you'd need 360 volts on the secondary to get the same ratio. Okay, if you have a 4-to-1 voltage step-down transformer, notice what they said. What would happen if it were essentially wired backwards? There's no reason you can't wire a transformer backwards. They're bidirectional. So if you apply a signal to the secondary winding, that means to the second side of a 4-to-1 ratio. So I'm going to draw that right now. 1, 2, 3, 4, 5, 6, 7, 8. Good. I can draw that. So that's 8-to-2, which is also 4-to-1, because it's about a ratio. If I have 1 volt over here, what will I get on the other side?
4.
Yep. And remember, this only works with AC. Transformers transform alternating current. So basically what they're saying is they're just hooking it up backwards. Again, you can do that. Okay, why is the primary winding of a voltage step-up transformer usually larger than the secondary? So here we go. It's a step-up transformer. What does that mean?
It's from
120
1
volts up to
yeah.
3,000 volts. What would you use something like that for?
Welder.
A welder? Well, I thought welders depends on what it is. You use this for a power supply for a tube amplifier. And then this is AC, you'd have to rectify that into DC, which you could do. So what would the turns ratio of this transformer be?
3,000 divided by 120.
Yep, which is 25 to 1 or 1 to 25. So if I have 1 amp over here, if I have 1 amp over here, how many amps do I have on the primary?
25.
25 amps. And we can actually look and see that the power is maintained. P is equal to I times E, 3,000 watts. P is equal to I times E, 3,000 watts.
Quick question, Scott.
Yep.
Does it matter if you're talking RMS or peak to peak voltage when you're dealing with transformers?
Just so long as you're consistent and so long as your peak voltage isn't high enough to puncture the insulation.
Thank you.
Whatever the protection on the windings is. Okay. Okay, next one. What transformer turns ratio matches the 600 ohm feed point impedance to a 50 ohm coaxial cable? All right. So remember, what happens to impedance? Impedance goes up or down as the what of the turns ratio? The square of the turns ratio. It's not proportional. It is the square. So if you want to change 600 to 50, that's a factor of 12. Your turns ratio would need to be the square root of that. So it's roughly 3.5. Okay, circuit components. All right. Given what we've already talked about today, why should you never use a wire wound resistor in an RF circuit that needs to be frequency stable and or impedance stable? A wire wound resistor is a coiled resistor. What's a coil of wire also known as?
Inductor.
An inductor. What happens if you change the frequency going into an inductor? What happens to its impedance?
Changes.
It changes. Okay, so if the impedance changes, your 30 ohm resistor might be 30 plus something, and it would be no longer 30 ohms. It would be something different. A 50 ohm resistor that we use for a dummy load, you would want it to maintain 50 ohms all the time. So we use non-inductive resistors for dummy loads. Low voltage ceramic capacitors, we use them because they're really, really cheap. An electrolytic capacitor is basically it's basically two aluminum foil plates that are separated by an electrolyte. Very, very high capacitance for a given size. However, because they're electrolytic, they have an electrolyte, they have a positive and a negative terminal. Has anyone ever hooked up an electrolytic capacitor backwards?
Oh, yeah.
Okay, electrolytic capacitors, they look like a little cylinder and they have like a little score marks on top because if you hook it up backwards, they will blow up and then spit all of the electrolyte goo out. It goes off kind of like a bullet. And you end up with all this foil uncoiled everywhere. It makes quite the mess. But at least it doesn't blow up outward. It usually just blows up in the direction that the score marks were made. Why it's important to do that. Okay, a ferrite core toroidal inductor. Okay, it's time to talk about ferrites again. We talked about ferrites a little bit yesterday. A ferrite is basically a combination of ferromagnetic materials, manganese, iron, cobalt, iron itself, that has been powdered and squeezed together with glue and baked into a donut shape. That's a toroid. It looks like a donut. By doing that, it makes it very, very easy to constrain a magnetic field within that material. That's typically a very, very good kind of material to hold a magnetic field. So magnetic susceptibility is much higher than other things, so that's why we use that, because it's basically powdered material mixed with glue. We can make them any shape that we want. Most of the magnetic field is in the core, large values of inductance, and optimized for a certain range of frequencies. The combination of different materials that we use, iron, magnesium, cobalt, nickel, changes the frequency response of that particular material. That's known as a mix. So we can change and select different materials for different frequencies. We can use ferrite cores to impede as well as to transform. So if we take a piece of wire like this, for instance, and we wrap this around a ferrite core multiple times, and it comes out the other side, what will happen is if there's a magnetic field at a given frequency that is now being carried and is circling, if you want to think of it that way, the wire, as we wrap it around the core, it will induce its magnetic field in the core. Depending on the type of core that you've picked, it might be such that that core tends to take that magnetic field energy and burn it off as heat. If that happens, how much comes out the other side? What do you think? If you took all your magnetic field energy, made at a different frequency, and burned it off as heat, how much is on the other side?
None.
No,
Nothing.
You have choked out your magnetic field energy, which has choked out that frequency. The current that made it is no longer able to sustain it, and you've basically gotten rid of it. You can also use it by terms of mutual inductance, where you take a core that looks like this, and wrap one thing around it multiple times and goes back out, and this multiple times and comes out this way. There is no electrical connection between those two circuits. This is a transformer. You're basically creating a magnetic field in that device, and the other wire, because a magnetic field is now passing through those turns, will induce a current and a voltage in the other wire. That is how a transformer works, like magic. Okay. What happens when an inductor is operated above its self-resonant frequency? Believe it or not, it actually inductors actually have a little bit of capacitance. They have their own, essentially it's self-resonant because it has a little capacitance as well as inductance. It actually becomes capacitive if you operate it above that point. Solid state diodes and transistors. Let's see how far we want to go today. I know we're going to go pretty far, but vacuum tubes, batteries, MMICs, display devices. Okay, we're cooking. We're cooking here. Everybody want to just plow through the next 20 minutes or so? I'm good with it.
Sure.
Okay, here we go. All right. So we are now into circuit components, and in particular, solid state diodes and transistors. Okay, a solid state device is typically built of a semiconductor material. A conductor is something that has a lot of free electrons. An insulator is something that doesn't. Semiconductors are somewhere in between. What's common about silicon and germanium is that their outer electron levels are both half full. So they can operate as an inductor, or sorry, as a conductor or as an insulator, depending on how they're put together. So what we do is we typically start with silicon And notice that if we put together a silicon diode, it has a forward drop of 0.7 volts. The way that this works is we take our silicon, which would be just Si, element number 14, and we take that silicon and we make this blob of silicon. To it, we add a couple of atoms that have a lack, like a missing electron, like phosphorus. Then we also would take another portion of it that might have a little extra electrons thrown into it. So now what happens is if we try to push current into this thing, we would have to, let's say we have pluses over here, we would have to apply a little extra push to make sure that it makes it to the other side. So we have to increase our voltage so that it can overcome the existing pluses and make it to the minus terminal. That is a what? Okay, so that's a forward bias. It causes a voltage drop. For silicon, it's about 0.7 volts. For germanium, which is another semiconductor material, it's about 0.3 volts. Just to get over that threshold. And that causes a voltage drop. So that's how a diode is put together. And remember that if you ever come across a diode, which you hopefully will at some point, you will see a stripe on this side, which is the negative side. Always hook that up to the negative side. And it indicates, schematic diagram looks like that, where current flows that way. Okay. A MOSFET, okay, metal oxide transistor, and it's a FET, which is a field effect transistor. Okay, so this is a device that internally looks like this. Where you have the gate and the drain and the source, like that. And when the gate has a voltage applied to it, that affects what's happening on the other side of this. What does that look like right there, everyone?
Capacitor.
That looks like a capacitor. So if I apply a certain voltage over here, that will put negative, it'll make it easier for negative charges to be over there. If I apply positive or negatives on the other side, that will allow positives to be over here. Depending on how this is wired, that will allow or disallow current to flow on the other side. So I change the gate voltage, and that basically opens up the path between the drain and the source. So the gate is separated from the channel by a thin insulating layer. It essentially forms a capacitive junction. We covered this yesterday a little bit. What are the operating points for a bipolar junction transistor used as a switch?
Saturation and cutoff.
Because the curves for a bipolar junction transistor look like this. This is cutoff, and this is saturation. This is your input voltage, and this is your output voltage. This is known as the linear range because it's basically a straight line. This is where you use, the linear range is what you use for amplifiers. Cutoff represents 0, and saturation represents a 1 for digital circuits. That's how we do computers. Okay, vacuum tubes. Woo! We still do vacuum tubes, believe it or not. Okay. So this is a vacuum tube, a very simple vacuum tube. Okay, this is known as the anode, and this is the cathode. The cathode boils off electrons, What charge do electrons have?
Negative.
Negative charge. Okay. So if we have this, this is known as, make sure I get it right. This is known as the grid. It can also be, it could be the screen grid. Essentially, what happens is that the cathode is a heated element. It boils off electrons. And if we put a positive charge over here, these will flow because they're negative. They're attracted to the anode. We will develop a current that flows up of electrons up through the tube. Right? We actually have electrons which are now floating across this vacuum. It is very important that the inside of the tube is made as a vacuum. So what do you think we could do with this grid to make it easier or harder for those electrons to float across?
Raise it or lower it.
Yeah, we can put either a positive voltage or a negative voltage over here. If this voltage is negative, right there, those electrons are going to be repelled by that negative voltage, and not as many of them are going to see the anode on the other side. If we do the opposite and we put positives here, they're going to be attracted and then be further attracted by the anode. So by changing the voltage on the grid, that allows us to change the current through the tube, which is the movement of electrons. And why do people still use vacuum tubes?
To heat their food.
They look cool.
High power. High power.
High power, yeah. Really easy to do high power because you're operating at very high voltages, which means you don't have that much current to deal with. Which element of a vacuum tube regulates the flow of electrons?
Grid.
The control grid. The purpose of a screen grid in a vacuum tube is it's an additional grid to reduce grid to plate capacitance. You basically have like another storage place for things to land. Okay, batteries. An advantage of batteries with low internal resistance is that you have a high discharge current available because they have a very low internal resistance. Now, that can also mean that if they're short-circuited, they can generate a lot of heat. They can cause a fire and stuff like that. So batteries, they're a good thing and potentially a bad thing as well, but mostly good. The minimum allowable discharge voltage for a 12-volt lead acid battery, you never want to get below 10.5 volts. Otherwise, you might have trouble recharging the thing. Analog and digital integrated circuits. Okay. An integrated circuit operational amplifier. Has anyone ever heard of an op amp?
Yep.
Okay. An op amp is an idealized amplifier that when it sees a differential between two inputs, it says, oh, it's a plus. I'm gonna turn on and say, yes, it's a big plus signal. If it sees a negative value, it's going to say, oh, I see a big negative value, and it runs a huge negative value. So an integrated circuit op amp is something that it can be used within a circuit to make a very, very easily controllable amplifier. So that's an analog device. An MMIC is a monolithic microwave integrated circuit. Microwaves are fairly small, right? They're microwaves. It's possible to put amplifiers and filters and things like that into a single circuit. So an MMIC is a microwave specific integrated circuit. Okay, CMOS is complementary metal oxide semiconductor compared to TTL. TTL is transistor logic. CMOS typically is what we use these days. It uses much less power than a TTL circuit. So that's the big change. All right, display devices and connectors. An LED is a light emitting diode. when it is forward biased, it emits light instead of just carrying current forward. Current goes through the junction and it emits light. Okay, which of the following connector types is commonly used for low frequency or DC connections to a transceiver? Has anyone ever seen an old school phono jack?
Yes.
Oh yeah.
They're typically red or yellow or white. Sometimes they'll be RG and B for a video signal. Those are your old school RCA phono plugs. An SMA connector is a threaded connector that's used for RF that runs up to several gigahertz. And it's significant because they are relatively inexpensive and they work extremely well up to very, very, very high frequencies. Somewhere here, I think I have even, maybe I destroyed it. I thought I had it here. Okay, let's see. RF connectors. I saw a really nice chart. Okay, here we go. We have all kinds of different connectors. Here's a UHF. Here's an MCX somewhere. A TNC. There's an SMA, SMB, N-type, etc., etc. These are used for various different things. Here's an SMA male, SMA female. You know, I once had an 11-year-old in my class, and he said, "You know, I don't understand something." I'm like, "What is it?" He's like, "Why are they called male and female plugs?" Like, you know what? We meet again tomorrow.
Ask your daddy.
Ask your mom when she picks you up. He's like, okay, I'll do that. And he came in the next day and says, oh, I understand now. So, so the important thing to note is that we have lots of different plug types and connector types available to us. Actually, the worst RF connector that you can possibly imagine is the UHF connector, which we use for lots and lots of different things. The UHF connector is your standard connector that's found on the back of most radios. It actually is only good to about 300 megahertz. If you want to go anything higher than that, you'll typically use an N connector, which is good up to like 5 or 6 gigahertz, or you'll use an SMA connector for smaller cables, which is also good to 4, 5, 6 gigahertz. Okay. So here we go. SMA, BNC, those are all good to like 4 gigahertz. An N connector, there you go, 10 gigahertz. All right, practical circuits. Okay, so being able to look at a schematic diagram and figure out what it's doing and what the components are. Okay, field effect transistor, that would be number 1. A Zener diode, look for something that looks like a letter Z. Ah, there it is, number 5. An NPN bipolar junction transistor. There's number 2. That's a bipolar junction transistor. A solid core transformer. Okay, where's a transformer in this circuit?
Number 6.
Number 6. Okay. Now, do you see something else that could also be used possibly as a transformer?
That inductor right there.
Yeah, that could be used. That could be used as an auto transformer. You're basically using one winding for 2 different things. But in this case, they're calling it a tapped inductor, which is number 7. Okay, power supplies. All right, we covered this a little bit. What portion of the AC cycle is converted to DC by a half wave rectifier? How many degrees are in a circle?
360.
So half wave would be 180 degrees. A full wave rectifier uses all 360 degrees. The nice thing about a half wave rectifier is that it is really simple. It's not as efficient, but it only requires one diode. A type of rectifier circuit using 2 diodes and a center tap transformer. You can actually do a full wave rectified power supply using 2 of them. The output waveform of an unfiltered full wave rectifier connected to a resistive load. Well, the reason that it puts out twice the frequency is that it flips the negative side of the sine wave. So if you have 60 hertz going into a full wave rectifier, you'll get twice the frequency coming out, which is sometimes why you'll get a 120 hertz hum. Output rectifier, let's see. Which of the following components are used in a power supply or power supply filter network? There are our old friends, the capacitor and inductor again. A power supply bleeder resistor. A power supply will often have a monstrous capacitor in it to do the filtering. By putting a bleeder resistor across it, it might take, 10 seconds to discharge or a minute to discharge. But what it does is that when you take the cover off, it won't give you a nasty shock. A switch mode power supply. Okay, a switch mode power supply is something that instead of operating at 60 hertz, will transform the frequency of the power that you're using to, let's say, 4,000 hertz. Because of that, because you're using capacitors and inductors, you can use smaller devices. Everything can be smaller. Has anyone ever heard about a switch mode power supply making RF hash?
They make my life hell at work.
Yeah, and why is that?
Just the on off of the switching network, it creates a lot of noise.
Yeah, exactly. And the reason being that basically the act of switching generates a square waves. Square waves contain a lot of harmonics. So if you have a 4,000 hertz wave, but it's a square wave, it contains 8,000 and 12,000 and 16,000 and 20,000 and 24,000. So that can be emitted as RF frequency energy, and it shows up all over the place. All right, digital. Okay, the difference between analog and digital. Analog has a value that can be anywhere between one thing and another thing, literally anywhere in between. Digital circuits have values of ones and zeros. So it's either on or it's off. So if I say I have a basketball and a football, what does that mean, everybody?
You have balls.
I have two. Yeah, okay. I have a basketball and a football. What happens if I lose the basketball? Do I still have a basketball and a football?
No.
No, right? Okay. So that violated the and. All right. So what if I say I'd like a basketball or a football, and somebody gives me a football? I'd say, okay, I did receive a basketball or a football. So the most common things to do are ands and ors. And sometimes there's NAND and NOR and NOT. But basically, these are very simple Boolean logic things. Boolean logic being zeros and ones. So an and means only be true if two different things are true. So I have a basketball and I have a football. So yes, it is true. I have a basketball and a football. If either one of them disappears, I no longer have them both. The output goes high only when the inputs are high. All right, so this is a clock circuit. It's a binary counter. These are pulsed outputs and inputs. And essentially when the clock turns on, when something goes to a true value, it turns on, and then it has another one and it turns off, which triggers the next one. This is a 3-bit binary counter. 3 bits can have 8 different values. Off. Oops. Where did I? Oh, come on. I lost my control there. Stop share. Let's try it again. All right, here we go. Last thing. There we go. So with 3 bits, I can have zero off. We have false, 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 001, 010, 011, all the way down to 111. There are 8 values, which is equal to, coincidentally, 2 to the third power. If I have 4 bits, all the way up to 1111, I have 16 values, which is 2 to the fourth power. 4 elements, 4 different things. If I have 10 bits, I have 2 to the 10th number of things, which is 1,024 different values, etc., etc., etc. Okay. A shift register is a clocked array of circuits that passes data in steps along the array. So the easiest way to describe a shift register is, oh, stop it. No, stop it. So if I have a bunch of bits and I have a 1 that's stuck in there, and I say shift it left, it would do this when I told it to. Or I could tell it to shift it back the other way. I'm basically just taking bits and I'm moving them from place to place. That's a shift register. And let's see if that's a convenient place to stop for the day. I think so. Because now we're getting into analog stuff. And so we've got oscillators and filters and transceiver design. That's a good place to start tomorrow. And emissions and modulation, frequency heterodyning. Let's see what else. We already covered that. Attenuators, high voltages, safety. And operating procedures. Okay. So yeah, I think that actually is a good place to stop. How do you all feel? Any questions? Overloaded? Overwhelmed a little bit?
I'm doing a lot better now than I was when I started this morning, so I think I'm doing okay.
Yeah, you've definitely covered the parts that I've been having trouble grasping just from trying to study on my own for the general. So definitely appreciate it.
Oh, good. And
A little overwhelmed, but I think if I go back and watch it, that it'll sink in.
Well, and I think one of the cool things, hopefully, is that when you go back and look at the question pool and look at the test and practice, it's like, oh, yeah, okay, this makes a little more sense now. So
the sad part is I passed my general 30 years ago. Remember that, and I never got per minute, so I never locked it in.
Well, I hope it's been helpful then.
Yeah,
it has.
Yeah. I've been studying my rear off, and like I said earlier, I took the test this morning. I passed it, but I still came because I want to actually reinforce what I've been studying. So,
well, and
I appreciate the class. So,
and that's the thing, studying for the exam is slightly different than studying for, than learning the material. It is a different thing,
Yeah.
I am one of those people that need to know the why when I'm trying to study, so it sticks in my head. I got plenty of people saying just learn the test and then you can learn the why after the test, and I can't study that way. It's a filter in my head. It doesn't allow that. So this is helping me
I'm the
understand.
same way.
Well,
I hate hearing just learn the test. No, I don't want to learn the test. I want to learn the why.
Well, it's funny because I learned it that way. I mean, when I was 17, I hadn't started college yet. I was in electrical engineering, but I hadn't even taken one class. And I mean, I went through electrical engineering, but I have the kind of unique perspective of having gone through and learned the exam all five, because there were five exams to take, and practiced for and studied the question pools and went through and passed the exam without really understanding anything beyond a cursory level. And then when I was in college, it covered all the topics.
Mm-hmm.
I mean, and so I was, I had some knowledge of it, but I was forced to learn the theory after the fact. So now, 40 years after passing my novice license, my novice exam, I can look at this and say, oh, well, I wish that I had had just a little bit of background information when I started,
Mm-hmm.
because it would have made more sense, other than, okay, well, I know the answer to this one is 625, but I can't calculate it. I don't know why.
Well, I can remember, if I have the basics and I don't memorize the question, at least when I look at the question and say, okay, I have this basic information. How would this apply to that?
Mm-hmm.
And that's why I need to have that background. I can't memorize the questions.
So when you get to the Canadian exam, when you get to the advanced exam, Alain, when you get to the advanced exam, it's going to be all of this.
Right.
Yeah.
but again, it's not soft stuff. It's it's hard. It's rigorous math.
Mm-hmm.
It's not maybe this or maybe this. It's rigorous mathematics.
Yeah, and I think that's good for me. I get a bit confused because I come from a different knowledge in terms of electrical stuff. Like earlier, you were talking about anode, cathode.
Mm-hmm.
I learned them a different way, so I kind of have to relearn that stuff and then relearn all the formulas.
Woohoo!
Mm-hmm. But
okay, well, you guys have a good night. I'm gonna head off. So, thanks. See you in the morning.
Thanks.
Yep.
The math and
See
the
you tomorrow.
electronics make sense to me. The antenna stuff is what just leaves me with my mouth hanging open most of the time.
How so?
I don't understand how they calculate. It'll say, oh, figure out you want to do this, and so you need this side to be the.
All right, let's do that. Uh-oh. Are you muted? Uh-oh. Where'd everyone go?
I'm here.
Yeah, we're still here. I think it's just her that got
I
muted.
think she dropped out.
Oh, okay.
She got muted accidentally. There she is again.
My friend, I live in Alaska, and he was saying, oh, you can put your antenna this way and go up over. And I'm like, my brain is just like, what are you talking about? Well, you just have to lengthen the one side. And I'm like, how? Why? The antenna stuff has just really got me.
Well, I mean,
going.
Really what it comes down to with antennas is, okay, so we're going to cover this too, but basically here's a dipole and the pattern looks like this. That's what the signal looks like. And when I say the pattern looks like this, essentially what that means is if you were to draw arrows, that represents how much signal comes off in that particular direction. So if we were to draw like a circle all the way around, that would be, essentially how much power is coming off in any direction. So right here at this angle, you would have this much power. And this is measured in decibels. At this angle, you would have this much power compared to your peak. So that's really all that means. And actually, this is something that we are going to cover too, because like, let's say, okay, so we have, typically it's done like this. And this is like a 0 dB circle. What does 0 dB mean?
No gain.
It means no change, right? So that's 0 dB. Outside of that, we can have a plus 3 dB. What does plus 3 dB mean?
Increase.
By a factor of 2 times.
Increase.
By a factor of 2 times. Inside, we can have a negative 3 dB circle. What does that mean compared to 0?
2 times loss.
Yeah.
But you lost 3 dB.
You lost half of it. No, you lost half
Decreased
of
by
the power.
2 times.
Right. And then you can also have a -10. And outside, you can have a +10. So when you're going to make your antenna diagram, your chart, your map essentially of what your antenna looks like, you have some antenna in the middle. And if it were uniform, it would have a radiation pattern that looked like this. That's known as an isotropic radiator. It has uniform and omnidirectional power output. So it would be the same in all directions.
But impossible to build.
Right, but that's impossible to build. That does not actually exist. So what we end up with is an antenna that has a pattern that instead might look something like this. Right, where it dips below that 0 dB circle for some of it, and it extends beyond the 0 dB circle for some of it, which means that if it extends beyond the 0 dB circle, you're going to have a little bit of gain. And if it's inside it, you're going to have a little less effective performance in those directions. Let's say we're looking at it from the top. Okay, so let's say you put together another antenna that looks like this. So compared to this circle, you're doing pretty poorly in that direction. Compared to this circle, you're doing pretty poorly in this direction, but you've designed the antenna in which you don't care about those directions because it's rotatable. In this direction, you may be outside, you might actually be at the 12 dB point. And the way we typically measure beam width is it's called the 3 dB point. So this compared to 12 would have to be 3 dB less, so that would be 9 dB of gain. This is known as the antenna beam width. And it's named by the 3 dB power points. So there's nothing really, nothing really magical about antennas. There's really not, other than the fact that they work at all. I mean, seriously, that's really what it comes down to.
Thank you.
But doing the analysis is really not bad, so long as you're willing to accept that there's just certain things about them that, that are just going to that are just going to work the way they say they're going to work. And after that, like I'll put up an antenna in my yard, and I don't really know how. I mean, I know how I think it should work. I modeled the thing using software. I know kind of what it's supposed to be like. And then I'll go and try it and see what it actually came up like. Am I making more contacts on the East Coast than I did before? If I built an antenna that is supposed to be working better than something else, and I find that qualitatively it's working better, then what does that say about how I did it? What do you think?
Means it worked.
It probably worked, yeah. I mean, my guess was right, you know. You start with theory and then build it, and then you test it, and hope
Make
that
sure you cut it long.
And hope that it drew you in, hope that it pointed you in the right direction. Scott, you got anything to add? It's been a lot of stuff going through the chat. I know that. Scott Gilbert, are you still there? Maybe not. Okay.
Yeah, he is. I was just having a chat with him.
Oh, okay. What would you recommend for a 30 amp power supply? Well, it depends if you want a linear supply or you want a switching supply. Astron stuff is always fine for big linear supplies that'll weigh 40 pounds. If you want something smaller, there's a lot of companies that make switching power supplies, and they're going to be self-contained 12-volt supplies. 35 amp supply will probably cost you $125.
God, did you want to talk to me about something?
Yeah, no, I wanted to know if you had any comments or anything.
Oh, no. Well, you did a great job compressing all this material. I mean, this is what I spent a couple of weeks on because it's so sometimes it to simplify it might make it harder to understand. So we go a little bit more into depth and maybe give a few examples. But I think you give a good overall coverage, and then I think it's up to the students to go ahead and go through the question pool and try to remember those questions. But the gentleman who made the comment about his learning style is he needs to understand it. I can relate to that. That's kind of the way I am too. I don't like to memorize stuff just for the sake of it. So, but I think you're doing a great job for the given them the amount of time. I mean, you're talking 8 hours here to give all this material. So, kudos.
So, I mean, just as far, and I guess I was asking whether or not you had any other comments regarding, any of the stuff we talked about too. I know that
Oh, I tried to.
I couldn't necessarily follow along with all the stuff in the chat.
Right. So what I did was I acted as a sidebar, kind of a information. I guess I was trying to supply that information on the side as somebody would read a book and then they see a sidebar and there'd be a little bit more in-depth information than what's in the main body of the book. So I try to do that, like say, give a little comment and say, well, yeah, by the way, this is kind of what, whatever it is. So that was what I was trying to do there. But no, I don't have any particular comments. I think, let me see, was there something I wanted to say? Yeah, the Smith, I think there was a lot of interest in the Smith chart, even though we couldn't really talk about it. But
yeah, the
it's kind of
Smith
intriguing.
chart, it is, if you're going to be designing antenna systems, it is definitely worth learning. It's not it's not that hard to learn. I mean, it looks a little intimidating, but it is a very, very, very useful tool for not having to go through all the calculations.
Exactly. And somebody asked, like, what would be the purpose? Why would you want to use the Smith chart? And I try to say that's kind of what it was developed for. So the idea of a slide rule, you don't have to, go through the math in your head. You just mechanically
Yeah.
do it, and there's the answer. So yeah, the yeah, no, but I think some of the students appreciated this getting the knowledge, and others were not so. It was hard for them to follow. So
Mhm.
but it's tough. It's a compressed course. It's kind of like a cram session. So
Yeah.
you can't, you're
But
not
that's
gonna.
also why I didn't do an exam after.
Yeah, no, I know the
But
students need time to digest this stuff.